Hello everyone, I would like to quickly introduce myself. I am Samir Abdo from Technical University. I am going to talk about analysis of aviation pollution in the selected regions of the world. This paper is done on the topic analysis of aviation pollution in the selected regions of the world. Here we are focusing on the various toxic emissions and the impact made by them in the atmosphere of EU region and the measures took by the various elites to reduce the environmental issues. The motivation for this paper is two levels of impact made by the aircraft to the environment of these innovation clusters made by in the country and to find the role of government in this issue. The paper consists of three parts. Mainly the first part is called theoretical part, where we briefly explain the facts and figures used. The second part, the analytical part, where we will do the analysis by comparing with two other regions such as US and Australia with EU. And finally, in the proposal part, we will showcase the finding and observation which we found out from this study and the proposed changes and results, which summarizes the paper. In this section, it will be followed the analysis of emissions, their impacts on the environment, and mention some studies which they deal with survey how to decrease CO2 emissions, case studies and findings. Emissions from the aviation industry are steadily increasing since the year 1990. There are no universal regulations for aircraft emissions. Emissions from aircraft are considered the lowest of all mobility industries. International standards were first proposed in 2017 and are expected to come into full effect by 2028. Here, if we are comparing to conventional fuels and sustainable aviation fuels, hydrogen is better because it eliminates carbon dioxide emissions quite, but also has the eventual to reduce other GHG emissions. Comparative with batteries, hydrogen has a high energy thickness, both in gravimetric and volumetric measures. The main advantage of using hydrogen technology is zero emissions. Another advantage is hydrogen fuel cell vehicle, and the growing interest is that it has comparable properties to conventional vehicles. If we compare the advantages and disadvantage of hydrogen compared to other sustainable aviation technologies, sure, the hydrogen will be a strong candidate for future propulsion. From the year 1990 till 2020, the emission rate was nearly a double figure when comparing with the figures from 1990. There is a uniformity in the emission rate from the year 2005 till the year 2017. As a result of the technological revolution and huge innovational changes that occurred to the aircraft industry, at this period of time, the emission rate was controlled or regulated with the necessary set of standards which reflected in a moderate rate of emission rate when compared to the other factors causing emission. Analytical part comparing between three continents EU, US and AU show the difference of CO2 percentage for each continent and the universal indicators. Comparison between EU and US. The US has 10% more emissions and also has the biggest aviation industry. There are no set of standards because of the US aviation policies are more favorable to the aviation parameters. Implementing the emissions trading system is what the European Union is working on the reduce emission. The US has stated in 2019 that it has been implementing regulations for aircraft too, but at a slower pace. Australia has a relatively small aviation market which emits about 24 MT. Australia has been making efforts for regulation since the year 2011, which the release of their action plan. There also have been efforts to make airports carbon neutral, which has already seen success in some places. Australia is also partaking in the carbon offset setting and reduction scheme for international aviation proposed by the International Civil Aviation Organization, similarity to the European Union. Until recently, the US government didn't make any steps in regulating aircraft emissions. Until May 2020, the market was completely unregulated. Because of that, airlines have seen an increase in fuel consumption paired with diminishing increases in fuel efficiency. It took several years and lawsuits for the US government to finally start acting. The Australian government has been implementing measures since the introduction of the 2012 action plan. They are also partaking in the Corsia plan with planned implementation starting in 2021. Australian government deployed some measures such as renewing their fleet to use the latest advances in technologies. Given more focus in investing into research and market development of sustainable biofuels. Proposal part. In this part, it focuses in some conclusion from the survey and analysis. For future, the aircraft traffic tries keep increasing of emissions. Finding and observation aircraft contribute only a very small percentage to the total amount of human-induced emission. Aircraft traffic is projected to keep increasing in volume. Research shows additional 60% or more increase in traffic and emissions going into the year 2032. The European Union has been probably the most efficient in controlling emissions and other environmental factors. Despite long periods of no action, in the recent years, efforts to regulate the aircraft industry have been put forward, with some countries taking the lead and some falling behind. Recently, there are no universal standards and no global ETS. Standards are being worked on and their implementation already started in some countries. A global ETS is not yet implemented. There are also no regulation except general noise regulation. World consensus is being formed, and countries are gradually implementing new regulations and innovating their technology. Recent developments and discoveries in engine and biofuel technology, coupled together with a global ETS alongside improvements in place such as airport production facilities. Our conclusion is that the authorities should focus on the implementation of global systems for ease of tracking and trading emissions. From the above study, we understood that the world is already moving on a faster pace on terms of technology advancement, and the aircraft industry across the globe is experiencing strong innovation changes. In addition, innovation in technology and approaches are essential to redefining mobility. Cutting-edge technology such as autonomous devices and ultra-light materials creates opportunities to transform the mobility system by enabling new business models and mobility services. After that, all focus should be shifted to implementing and enforcing so-called regulations using data from the global system to reach the projected milestones. Thank you for your attention.
Hello, my name is Stefan Hensel, and I want to present to you our contribution object detection and mapping with an unmanned aerial vehicle using neural convolutional networks, which was done together with Marian Marinov and Max Schmidt. First, I want to give you a small intro and motivation. Afterwards, I want to show you how object detection is done with the deep neural networks. In a third step, I want to explain our system setup, how we solve our problems with that hardware, unmanned aerial vehicle, neural network framework, and the system integration, which we are using ROS for. And then I want to conclude my talk with experiments and an evaluation of our findings. First, for the motivation, object recognition and localization from above is a widespread problem. For example, very important is search and rescue, where you can think about problems after catastrophes or natural disasters, where you want to either find some victims or want to control and help the search and rescue teams. Another popular demand is given on high seas, if you have some situations where you want to find sailors, or if you want to sleep at night and want to detect possible traffic accidents. So whereas this is search and rescue, we have a lot of surveillance tasks which can be thought of, for example, here in the precision agricultural field, where we want to detect these weeds which are not wanted here beside the true fruits and harvesting we want to conduct. On the other hand, a lot of research topics are going on. Here, for example, if you want to track some mammals in deserts or mammals here in the open seas or oceans, it's highly comfortable to use the site from above and have some kind of automated object detection. Whereas this has been very restricted in former years, nowadays we have low-cost platforms at our disposal, where we want to show you here with the quadrocopter, for example, where we can access a lot of more broader applications, which has been out of reach before. As well, want to show an easy acquisition and deployment, which means you can have no problems. We have all out-of-the-box solutions, and we have some comfort functions for this. And another important topic here is robustness. So if you want to ensure that you find typical objects or problems, we can use low-cost platforms to get this robustness by employing several swarms of these drones and unmanned aerial vehicles. So if you use 3 or 4, you get an inherent robustness and are still much cheaper than some professional solutions. Here again is some example of precision farming where we have a banana stock implementation. So our problem definition is to set up a system designed for low-cost drones in combination with camera-based object detectors for a multi-purpose object recognition and localization task. Here we mean that we localize this in a global reference frame where we can find it afterwards, where the object recognition is done purely optical. We were identifying several problems where we can show and demonstrate our problems, and we were deciding for a parking lot surveillance. So this is, we want to determine the capacity, for example, or you can control parking fees, you can find out theft, and so on. So there are several possible applications in this scenario, and due to the autonomous driving situations, you can also think about surveillance of these parking lots to coordinate the parking space within a city or anything where you can connect with automated driving fleets. In addition, we have no problems concerning privacy for the network training, which means you don't have to capture people or anything, and you still have a valid problem. And nonetheless, we can show the setup and the workflow, which is capable to be adopted for all the other tasks you can think of, as I have presented before in our motivation. First, some fast words for object detection with deep neural networks. Neural nets are basically a mathematical model consisting of neurons as atomic building blocks. This means we have here an input signal, which is multiplied with a so-called weight. And then we are summing up all these inputs. So we have a linear combination of these inputs. And then very important, we are assigning a nonlinear activation function. And this activation function can be anything, but it's commonly a so-called rectifier unit. And you have an output of this neuron. Now, this is called a neural net because this has a slightly resemblance to our brain system. So you can see here a biological neuron, and here you have a nucleus and a soma, which is adding up all these incoming signals, which is a little bit like here with a summation, and you have these axons, which are going to the next neuron, which is here the output signal, and here you have in this axon hillock, you have this nonlinear activation function. So this is basically the building block. And if you want to do some complex function approximations, you're combining these neurons and stack them into so-called layers, and then you get a multi-layer perceptron or multi-layer network. You have here input layers where the signal is going in, you have some hidden layers and an output layer. If you have only few of these, we are calling these neural networks, and if you have several of these hidden layers, commonly above 5 or 6, there's no real number here for this. We are talking of a deep neural network, which must be trained with deep learning methods. As images are represented by a high-dimensional data, we have the problem that this classical approach is not quite feasible. So we are using here in image processing or computer vision convolutions. Convolutions are an element-wise product here of these tensors. So you can think of this as a gray value image, and then you have a so-called kernel, and this is moved over the image and building up a weighted sum of this region. This has several advantages. The most important one is that you are vastly reducing the numbers of parameters in your neural network. The other one, that you have some locality in here and you get a translational invariance. So you are able to detect, for example, corners in the upper left and in the lower right. The output of this process is a so-called feature map. So if you think about here, this was the typical layer architecture we had before. In computer vision, we are working with convolutional neural networks, and here we are replacing these layers with our filter kernels, or better said, the weights are replaced with the filter kernels, and then you get these feature maps. And they are basically, you have here an input tensor, which is the size of the image for 3 for the RGB channels, so you have color images. And then you decide by a parameter how many of these feature maps and what dimensions they have. And the output is commonly something like a class probability, where we say car or ape or whatever. Short word on a hierarchy. We are not doing here classification. This means you would have to have a single object in an image and would say here dog, for example. Then you have the classification and localization task. Although we are speaking here of localization, we are meaning this in a metrical sense, not within the image here. So from a computer vision purpose, we're doing object detection, which means we have possible multiple objects within one image and we want to define their position. A little bit more complicated would be instance segmentation, but for our scenarios we are looking at, this is not necessary, as we want to only find the object and not the pixel-wise segmentation of this. With this small introduction, I want to explain to you the system setup to put this all together. So we have a neural network object detection we want to do. So these convolutional neural networks are basically capable of doing segmentation and classification and all. We want to do detection, and we want to combine this with a low-cost unmanned aerial vehicle. For this, we chose a low-cost quadrocopter, which has the benefit of having a pricing below 500 euros. And we were deciding here for the Parrot Anafi drone, which has an open source Python framework we can employ and integrate in our system. There are several advantages of this system. First, it's only weighing 200 to 300 grams, so we need no license for flying. We have a 4K camera optical resolution, which we can face downward or in front, so it's a controllable camera. We have a fully integrated flight controller, which means if we do nothing, the UAV is just hovering above for example, our parking lot, and it's not falling down or anything. We have a transmission range of up to 4 kilometers, which is enough to cover also large parking spaces. And we have a maximum horizontal flight speed of 50 meters per second. So this is important because not we want to fly very fast, but this is basically the maximum limiting wind speed we can operate in the parking lot, because velocity of wind is a disturbance for our positioning system. Although it's a low-cost UAV, we already have a satellite positioning system, so-called GNSS, and we are employing here GPS and GLONASS, so we have a lot of satellites available to determine our position up to 1 meter accuracy. For the object detection, we were looking at several solutions, and we were deciding for a so-called single-shot detector. And here, this is the so-called YOLO detection framework. This is the only loop once from 2016. And the first version, which I'm showing here, is to explain shortly the idea which is employed here. So you are subdividing your input image into a grid of size S cross S. Here, for example, it's 7 cross 7, which is also the size of the basic architecture. And then you are predicting for each of these cells here a class probability, for example, here dog or here bike, and 2 bounding boxes, which have a possible resolution here. The important thing here, this is a so-called single-shot detector, which means you only have one neural network, one output, one input. You can train this in one flow. And the big advantage of this, it's very fast compared to a 2-stage detector, which is also a possibility. Here you see the output then is a so-called bounding box with a class probability. Here a bike, here a dog, here a car. For this work, we were doing some evaluation here for the function of how this is working, that you get here the conjecture to the convolutional neural network is the following. You have here an input image, which is a color image of size 448 cross 448 pixels. And then you have all these convolutional stages going down here to the end. And then you have 2 so-called fully connected layers, which are analogous to our multi-layer perceptrons. And the basic idea is here you get this output block, which has size 7 cross 7 cross 30. The 7 cross 7 is this here. So you have 7 cross 7 pixels basically in this feature map, and each pixel has associated with it the 2 bounding boxes and a class probability. And because this was trained on a basic set with 20 classes, you have here an output of 30, which means 20 classes plus 2 bounding boxes, each with 5 parameters. In our case, we were adopting this for the cars, so we only had car and no car, so we had basically 2 classes. We chose several architectures here and evaluated these, and we came up with a YOLO for 3 version, because you see here we have here these single-shot detectors. Here SDN is a 2-stage detector, and the newer ones here we were deciding for YOLO version 3. You see here a trade-off between how fast the system is, how accurate the system is, and you see here at the bottom. Although we have other systems which are as accurate as YOLO or even more accurate, like the RCN setup here, YOLO is much faster. So we have here a factor up to 8, and compared to the other single-shot detectors, we have a factor up to 4, which we are faster with a better accuracy. So it's easy to learn, easy to implement, because it has an own framework for training, and we chose for this applications YOLO version 3 with an input image size of 416 cross 416. To integrate all this, we need a so-called middleware, because this is a Python framework for the UAV, and we have to adopt this neural network framework. We need some flexible software and modular development to be able to use this for different UAVs and to adopt this for our needs. And we have multiple language support, which means Python and C++. And it's distributed, which I will explain in a moment, which is very important, and have a proven tool chains. So visualization, simulation, locking can be done. We have a large community giving us the drivers and hardware for several optical systems and UAVs, and we are choosing ROS for this. This is a so-called middleware, sustained by the Open Robotics Foundation, and This is how we integrate the system, and the overall setup for our system then becomes a distributed system, which means we have a quadrocopter, which is doing attitude control with all the sensors within the system. We do the localization based on a GPS system, and we have the data acquisition. So we have a wireless connection and just taking the images. So basically we are using the onboard sensors for flight control, but transmitting the images to our base station. And the base station is running with ROS, which gives us a possibility to have a neural network-based detection in the system. This is GPU accelerated, which means it's very fast and working in real time for our purpose. And we can do some path planning and navigation, which is provided by the community. And we have a lot of interfaces here, for example, for bus systems or GUIs, where we can display the maps with the vehicles. Okay, with this setup, I want to show some experiments and evaluation. And we were using here a pre-trained YOLO v3 network. Pre-trained means it's generically trained on a large data set on the internet, not on cars. And then we are doing transfer learning, which means we need a quite small sample size of roughly 300 labeled cars. You see this, so somebody has to take pictures with a drone here and label these images. And then we have only these few training samples and get a mean average precision, which is basically accuracy of above 94% for our scenario. A result is shown here. So this is a labeling, and then you're flying or hovering with a drone, taking 20 pictures, and you see how many cars are detected. So here's the position of the UAV, and you see here how the cars are detected. They are very precise here. There's no wind going on, and you see very accurate working here. There's also some metrical accuracy, which is ongoing work, which we are doing at the moment. So if you know where your drone is flying here or your UAV with a GPS system, you can compare your detections here of the cars, and you see this is very neatly lining up here. So we are capable of finding a car and placing it on a parking lot. There are still some problems if you are flying too fast or if you have strong winds. You have no assumption that your UAV is hovering above the parking space. So if you're flying here in small curves, or if you're just here with a lot of disturbances, you see that the parking lots is a little bit more unclear. So we are doing in the second step, which is programmed in Python and ROS, the so-called non-maximal suppression. And for this, you have to take the bounding box into account and do a covariance estimation with the clustering algorithms, and then you get the parking positions. So I want to conclude my talk, and I presented a low-cost object recognition and localization system, which is based on this unmanned aerial vehicle here. We have chosen, trained, and evaluated a deep neural network for this object detection task, which is called YOLO v3, which is fitting perfectly with our middleware and our system. We have an exemplary solution for the cars in the parking space with an accuracy of roughly 95%. Also, we are using a lot of frames. This is basically a total coverage of all parking cars. It's easy transferable to different applications, for example, livestock or rescue missions or so on, or finding some weeding or farming stuff, because you only have to change your network weights and train them. Instead of cars, you can train them on cattle, and you can surveil your livestock. Ongoing work in the moment is that we want to further enhance our localization capability with GPS, so we need to combine the GNSS system with our camera, so we have a coordinate transfer system, and we improve the metric localization so we can have on-the-spot solution to find all our cars or animals or whatever. With this, I want to conclude my talk, and I thank you very much for your attention. If you would have questions, I would be honored to answer them. Otherwise, don't hesitate and write me an email. Thank you very much.
Hello, my name is Goran Jaushovac and I come from University of East Sarajevo, Faculty of Transport and Traffic Engineering, Doboj, Bosnia and Herzegovina. I am a lead author of the paper Smart UAV Monitoring System for Parking Supervision. Other co-authors on this paper are Dalibor Dobrilović, Vladimir Vrtka, Gordana Jotanović, Dragan Peraković and Željko Stojanov. Our email addresses are presented on the first and last slide so that you can contact us due to paper-related information or future cooperation. The increase in number of vehicles causes a problem with parking space. Parking vehicles becomes a big problem because there is often shortage of parking space. Very often the public areas are used for parking the vehicles. One possible solution is monitor public areas with fleet of unmounted area vehicles to prevent this. Unmounted area vehicles or drones have numerous applications in the urban world today. Drones can be classified into different types based on their design, size, cost and flying mechanism. Secure coordination of many drones with their autonomy in performing tasks is the topic that has interested many researchers. To use drones in area detection and monitoring, we must first create secure, reliable network in which drones can fly undisturbed and send images to base. The most often used networks for communication of drones with the base are Wi-Fi and LTE networks. For monitored application of drones to become operational, it's necessary to create systems with drones that use artificial intelligence and machine learning algorithms. On that base, we perform continuous monitoring of public areas. Designing a system architecture in which drones would fly predefined trajectories and coordinating a network of drones to cover urban areas is not an easy task. This paper proposed a prototype model that solves the problem of observing and supervising drones' predefined trajectories and communication between drones in urban environments, where there is static and dynamic obstacles. The architecture of Smart UAV Monitoring System for Parking Supervision, or short Smart UAV PS as we call it, is presented in next section. The Smart UAV PC consists of a fleet of drones that communicate with control center to detect and identify improperly parked vehicles. The proposed system architecture consists of three components: fleet of UAVs, communication system, and control center. The fleet of UAVs refers to a group of 3 or more drones working together to achieve the same goal. The system is automated and operates with the help of observer UAVs and inspector UAVs. The purpose of observer UAVs is observation of public area. Observers move along the defined paths at altitudes of 30 to 70 meters above the ground. A takeoff performs according to the predetermined schedule. On the one route can be deployed several observers. Those drones take in turns one by one, and the time difference in starting the drone depends on the number of drones deployed in a specific route. A higher altitude is necessary to avoid drone detection and reduce number of static obstacles by designing the drone's trajectory. Observer takes images of monitored area current state and defines location. After capturing images, he sends them via wireless networks to control center. The observer continues its route to the next defined location, or if it is on the end of the route, it flies to the UAV docking station. In docking station, observer drone recharges his battery and flight reports upload to control server. Inspector UAV has task for examining the location where the incident is detected. Using the location and the route to the location data, the inspector goes to one or more inspection locations where he takes videos and images. He arrives at position in dynamically defined trajectory forming control center. When the inspector reaches the position, he descends to height of 3 to 5 meters above ground to perform more detailed inspection of the location. Location snapshot records on SD storage. After finishing inspection at all defined areas, it returns to UAV docking station, where he uploads the data, reposts logs, and recharges the batteries. The data collected with help of inspector are used to initiate further forensic actions. Communication system. Design of public areas monitoring and surveillance system is oriented as UAV to infrastructure communication. It is because communication between drones manages with the assistance of control server located in the control center. The elements of the communication system are gateways, network infrastructure, and UAV docking station. The gateways have essential role in maintaining drones' connectivity with control center. Considering the drone's mobility, the aerial part in the urban environment with the numerous obstacles, the real image transfer from observers to control center is challenging. Also consider the location of system deployment and terrain configuration. The network infrastructure have supported for roaming homogeneous and heterogeneous networks. The UAV docking station is a fully automated system that serves drones. The station is a precisely specified place for safe vertical takeoff and landing of drones. In addition to this function, it should allow fast recharge of drones' batteries and establish communication between control center and drone. It would be desirable for the proposed system to use static station with fired connection of control center and electric infrastructure. The control center is the brain of Smart UAV PS. The elements of control center are control server, application server, and data storage. Besides drone coordination, this control server receives data from drones, stores data in database, performs analysis with machine learning algorithms, and performs further processing. It should have high data processing ability to process images and process algorithms for defining drones routes. The image sent from drones to control center is analyzed using convolutional neural network, or CNN, to detect and suspect traffic situation in public areas. The role of CNN is to classify the traffic situation. The case study was conducted in the city of Doboj, Bosnia and Herzegovina. Doboj is a city under 1,100 inhabitants with many public areas. These areas usually are used as parking space. The area of city settlement of Doboj is 10 square kilometers. Because it's large space, surveillance areas need to separate into sectors. Separation into sectors is defined considering drone characteristics. In sectors, air corridors for drones based on their precise defined critical points would be forwarded. For experiment, we chose Vojvoda Mišić Street in Doboj, where we defined 5 critical points to record from case study. The image taken points are determined based on the observer irregularities in public areas within the street, and the Faculty of Transport and Traffic Engineering proximity, where the gateway's location is, to achieve wireless communication with drones. For recording, we use 3 DJI Mavic Air 2 commercial drones. 2 drones were used for observers, while 1 drone uses as inspector. Drones' trajectories were defined from the control center to the observed street and back. The chosen place for control center is building of Directorate of Development and Construction of City. The location is chosen for control center because it's the center of city zone and has all necessary infrastructure. The location of control center is optimal for implementation of smart UAV PC in city of Doboj. For case study, we performed 4 flights according to the defined trajectories. Recording of the images in defined points on this trajectory performs from height of 5 to 30 meters above the ground. Significant problem with the use of drones, such as impact of weather conditions, the problems of opticals, technical limitation of drones, and battery life were taken into account. Nevertheless, the proposed concept is acceptable from the point of view of drones operating and communicating with the control center. Wireless communication use gateways and TCP/IP network infrastructure proved to be successful. The special problem is collecting images because the number should be sufficient for the neural network's successful training. This is a significant problem because it is impossible to use fleet of drones in more extended period due to financial and safety reasons and legal regulation. However, the proposed CNN architecture requires excessive resources. The accuracy on the training set was 0.90625, while the accuracy on test set was 0.875. High time memory consumption is not acceptable in applying the situation awareness model, so additional downscaling of images is needed. The system's rapid response is necessary because the drone fleet on the circular path will transfer the data to server, where further training of CNN is performed. It's estimated that the system needs to react within maximum of few tenths of minutes, so CNN training must be fast, given the drone's cameras will collect large number of images. Recorded images, recommended images for use of CNN training range are from 32 by 32 pixels to 512 by 512 pixels. Of course, higher resolution are possible, but these cases are rare. Also, it's possible to use more channels, which further increases the training time. Experiments were performed on grayscale images for following resolution 32 by 32 pixels, 96 by 96 pixels, 128 by 128 pixels and 256 by 256 pixels. Also, the number of epochs was varied. The validation of achieved result was performed using accuracy. Results are summarized in the following table. Based on result of table, it can be concluded that images resolution from the training set higher than 128 by 128 pixels are not suitable because the training time is too long and on average hardware configuration. The lower resolution remains, but it's evident that the maximum accuracy is 0.875. This clearly points us to the case of 32 by 32 and 100 epoch of training. Although it remains to check the time of training in the case of more extensive training set. Also, the accuracy of 0.875 is not so high, so there is additional adjustment of CNN and better selection of element of training set. The paper presented the results of experimental application and partial implementation of new system concept for smart UAV PS. The aim was to propose a basic concept of system that ensures scalability. The proposed system is scalability refers to centralization of drones control and application of smart UAV PS in image processing and machine learning applications. It has been shown that it's possible to handle a fleet of drones on experimental example. Several cases studies have undertaken, one of which is described in this paper and relates to drone use to identify illegally parked vehicles from images collected by drones. The recognition task is performed using CNN. It was concluded that images low resolution allow successful recognition on small data set. Training set accuracy was 0.9375, while test set accuracy was 0.875. It is clear that achieved accuracy is not enough, so the system must be scalable. The presented case study confirms the applicability of proposed concept from the point of view of network infrastructure and drones' role. Namely, there are two roles that drones can play. Observers are in charge of recording situation, usually from height. If irregularity is noticed, the inspector drones will be sent to location to take further action for lower height. This concept allows saving resources in terms of minimizing the duration of flight. The equipment needs, but the main contributor relates to possibility of centralized management of the entire process and scalability. Centralization in this case has several advantages. It's possible to manage multiple fleet of drones operating simultaneously in different parts of city, even in different cities. It is possible to share resources as well as easy upgrades of hardware components. It also impacts further upgrading the system in terms of number of drones, trajectories, and resources required to implement a convolutional neural network. From all of the above, it's clear that it's necessary to improve system and perform additional research of experimental in real conduction. Further research in this area will result in additional improvement based on various experimental scenarios on possible application. Regarding the system's software architecture, further work will be directed toward implementing a layer service-oriented architecture where there will approved service for different devices, systems, and users. Improvement of the system architecture could be a module from the detecting irregular situation in vehicle parking and traffic. Also, algorithm of routing drones may be subject of further research. Special attention will be on research of the secure challenges of applying drones in urban areas. Thanks for attention. If you have any questions, feel free to ask them.
Good day to all. My name is Petra Zoric, and today I will present you a paper entitled Information and Communication Architecture of the Passenger Information System on the Railway Network of the Republic of Croatia. I wrote this paper with co-authors Dragan Peraković, Marko Periša, Marijana Petrović, and Ivan Cvitić. First of all, I will say something brief about myself. I'm currently employed as an assistant at the University of Zagreb Faculty of Transport and Traffic Sciences at the Department of Information and Communication Traffic. I'm also a PhD student and I'm developing my knowledge in the Laboratory of Security and Forensic Analysis of Information Communication Systems, which is part of the mentioned department. My scientific work is focused on researching the possibility of applying information and communication services in different segments of the transport system. I also had a role in organizing this year's conference as publicity and social media chair status. The review of the research consists of the following units: introduction, analysis of the current state of telecommunication infrastructure on the railway network in the Republic of Croatia, analysis of transport demand on the railway network of the Republic of Croatia, proposal of the conceptual architecture of the passenger information system, and conclusion, of course, as the last part. The length of railway network in the Republic of Croatia is 2,617 kilometers, and the lines are classified into lines for international transport, regional transport, and for local transport. The infrastructure manager in the Republic of Croatia acts as station manager, and it is HŽ Infrastructure Ltd, whose responsibility is to provide the user with train departure data at railway station. Passenger information systems implemented on the EU railway network are based on modern information and communication solutions. The passenger information systems architecture is possible to perceive through the elements located at the station, stop, or platform, and, of course, in the vehicle. The architecture can be presented through 4 levels: application center, digital solution at the station, communication between train and track equipment, and digital onboard solution. According to official data, there are 545 passenger stations for reception and departure of passengers on the Republic of Croatia's railways network. Each official place also contains specific technical characteristics such as area for reception and departure of passengers, or station stop buildings with or without waiting rooms. Type of safety and signaling systems are shown in this figure on slide. The communication infrastructure consists of the following elements: telecommunications and electronic devices, telephone devices and method of registration, radio devices, teleprinter and fax machines, types and manner of use of telecommunication lines, receipt and dispatch of telegrams, intercom and public address devices, IT devices, railway automatic telephone switching office and ways of intermediation, and telecommunication and information devices and lines. The research analyzes the state of communication infrastructure for each official place: type of telephone use, type of radio, fax, teleprinter, type of and method of using telecommunication lines, method of receiving and sending telegrams, intercom and public address devices, telecommunication devices, IT devices, and part of the analysis was shown on table of the previous slide. Train traffic, which includes signaling, regulation, reception, and dispatch of trains, and communication related to train traffic on the railway network, is managed by signal safety devices and telecommunication devices. An overview of the types of telecommunication devices on railways network is shown in figure on this slide. According to official data, 124 stations and 132 stops are equipped with systems to provide visual information to users. Dynamic passenger information is provided via screen at 6 stations. The current systems for providing information to passengers on the railway network managed by HŽ Infrastructure are EXOR and EKGIP1. Information and communication infrastructure equipment analysis for each official position was made according to the assessment of the condition and existence of passenger information systems with info boards, loudspeakers, clocks and the manufacturer, cable tubers, concentration and connection of the official place with the railway cable, on-site electricity connection, possible components of the passenger information system. Part of the conducted analysis is shown in table on this slide. The analysis of transport demand on the Republic of Croatia's railway network includes passengers dispatched by long-distance, local and suburban trains based on available data. In the Republic of Croatia, most passengers depart from Zagreb Glavni Kolodvor station, which is expected given that most passenger trains start or end their journey at Zagreb Glavni Kolodvor station. The first 10 stations with the largest number of dispatched passengers at the stations and stops that are part of the Zagreb city's suburban traffic are shown in this graph. The analysis showed that passengers from 498 stations and stops were dispatched in long-distance, local and suburban trains. The total number of dispatched passengers in these types of trains is 90,007,099 and 362 passengers. On the Republic of Croatia's railway network, 355 passenger stations dispatched between 1,000 and 100,000 passengers, while 66 official places dispatched less than 1,000 passengers during the timetable period 2018-2019. It is a devastating fact that 41 official places did not dispatch a single passenger based on the conducted analysis. A total of 1,800,013 and 83 passengers were dispatched in long-distance transport during 2018-2019 timetable period. The smallest number of trains was sent between Pula and Rakitovac, where trains do not run all year round. The average occupancy of long-distance trains for timetable period 2018-2019 is 52%, depending on the time of the year. For the passenger information system's reliable and efficient operation, the subsystems that are needed are automatic train control, automatic resolution of incident situations, timetable monitoring, ticket sales, and maintenance. The passenger information system needs to be integrated as a subsystem or module of the future operational management and traffic control center, which is a prerequisite for developing a system that will enable fully automatic traffic management. On this slide is Operational Management Center, whose goal is to achieve organization and greater efficiency of executive staff, regular traffic, reduction of train delays, more straightforward elimination of traffic disruptions, and providing information to system users. It consists of system servers, such as communication servers or web servers, and computer programs and applications to inform users. Modern solutions in this area are based on IoT technologies and sensor networks. The current state of the communication infrastructure on the railway network in the Republic of Croatia can lead to high initial cost of implementation and the complexity of integrating new systems. The advantages and opportunities that technologies such as cloud computing and IoT and modern communication and sensor networks can provide in the environment of railway infrastructure management are shown in this figure. Such an approach creates a smart infrastructure within the railway system. The passenger information system is an integral part of the operational management and traffic control center. All data necessary for users' real-time information and the possibility of pre-trip information must be part of a central database. The conceptual architecture of the system is based on the concept of cloud computing and IoT sensor technology. It is an integral part of the system's central units or servers in the operational management and traffic control center. All the data needed to inform users is in the cloud computing environment. These options apply to people with disabilities who require adaptation of the content depending on the degree and type of their disability. Databases that are an integral part of the architecture contain data on trains, official places, and incident information. All relevant data are processed and included in appropriate applications. Communication servers serve as a mediator in exchanging data between central and peripheral units of the system in real time using different protocols. Data communication should be based on mobile 3G, 4G, LTE, and 5G technology, and of course wireless and wired technology in the access segment of the communication network, depending on the capabilities and technical performance of the communication infrastructure. Web servers allow users to access web-based applications on the local network. Traffic controllers' workstations are computers through which traffic controller in the operational management and traffic control center carry out supervision and management of overall traffic entities for which they are responsible. Workstations consist of computers, screens, and voice communication equipment and contain all the necessary computer applications to monitor and manage traffic. A user database is used to manage user profiles, where all data about the users, or in this case passengers, are stored. It is also possible to integrate with other forms of passenger transport if it is integrated passenger transport. All official places information comprises information on the monitoring station and all stations under its supervision and management. Information on additional facilities and the possibility of connecting with other forms of transport can also be part of this functionality. The development and application of 4G and 5G communication network in the railway system leads to more reliable system operation. In contrast, BSN networks can be used in object identification in the station and stops environment. The condition of the communication infrastructure on the railway network in the Republic of Croatia is not satisfactory. Thus, based on collected and analyzed all relevant data necessary for defining the functions of the elements of the central passenger information system, the conceptual architecture of the system was proposed. This system is an integral part of the operational management and traffic control center and is based on the concept of cloud computing and IoT sensor technology. Future research will focus on the types of information needed for the transfer and information of passengers and the phases of the introduction of this system of passenger information in the Republic of Croatia. Feel free to contact us if you have some questions about this paper and or this topic. Thank you so much for your attention. We're also always open for new collaborations, so don't hesitate to contact us. Once again, thank you for attention and enjoy in the rest of the conference.
Good day, ladies and gentlemen. Let me please introduce myself. My name is Patrick Schwab, and I'm from Faculty of Aeronautics of Technical University of Košice. Today, I would like to present you the intention behind our article, the utilization of renewable energy sources in the construction and maintenance of transport infrastructure. First of all, short contents of my presentation. We'll go through the introduction. What does it mean, Intrusion, thermal transformation system, the functionality of solar road system, or SRS, advantages and disadvantages of this system, its utilization in airport construction. I will present the conceptual model of airport with SRS implemented, also practical application of the system and methodology of elimination of icing phenomena using SRS. Also, at the end of the presentation, it will be conclusion. It is a well-known fact that black surface has a high tendency to absorb sunlight and its rays. This absorption is manifested by a heated black surface. In the summer, we can observe and physically feel the heat waves that are radiating from the overheated concrete or asphalt. It's not surprising that there have been some attempts to recover or utilize this heat accumulated in the upper layer of whether it be concrete or asphalt. But the initial efforts to construct the roads or other transport infrastructure from solar panels met with the problem. And this problem is with the bearing capacity and durability of these panels. The panels would not be able to support the weight of heavy machinery and would not be able to support the weight of, for example, if we are talking about airport construction, it would not be capable of bearing the weight of whole aircraft, and not talking about multiple aircraft at a short time period. So this ruled out the use of solar panels in airport or other transport infrastructure, construction and maintenance. Therefore, efforts to use the thermal energy accumulated in concrete and asphalt has been partially halted. But this alternative to using to utilize a renewable energy source has not been forgotten. This accumulates in the establishment of the ICEX project. ICEX is an acronym that means Intersessional Collection and Exchange. And this project has focused and still is focused on the use of renewable energy sources, mainly in transport infrastructure construction and maintenance. The concept of using infrastructures to collect solar energy is called solar road system. It's like the main idea of this project. This project joined a global organization called EHAB, which has the same focus. In the combination, the use and improvement of roads and other transport infrastructures, in addition to their primary task and the primary test of the system also provides the possibility to use the area for collecting energy from renewable sources through the integration of technologies. These technologies, we call them heat collecting, were developed within this project. The concept of using the solar energy, as I said, is called solar road system and is already in use in several countries around the world. For example, Denmark, Germany, Switzerland. At that time, it was approved after testing in external conditions, and it fulfills all the requirements, whether it is bearing capacity or technical standards in specific countries. So what is the interseason thermal transformation system? It is a complex system of heat collecting pipes incorporated between the individual layers of the road or other transport infrastructure. The first part of these pipes is located just below the top, the bearing layer of the road, and the second part is called thermobank. It is the part where the heat energy that is accumulated from from the surface is dissipated by the pipes, and also this energy is stored in this component of the system. The whole heat transport is ensured by the fluid with which the individual pipes are filled, and the pipes are made from polyethylene and are placed and fixed on steel grids. Thermobank is usually located in the bottom layer and is embedded in sand or other material that will provide isolation from the environment, so there will be no loss of heat or loss of accumulated energy. Above the polystyrene, which is the insulating layer, there is also a layer of granular material which has the task of absorbing water. This is so that it does not get into the next layer and do not cause any damage or any errors in the system. Unlike conventional devices where any type of energy is stored, a thermobank can contain heat and this thermal energy for several months. With conventional equipment, there is one problem that a large heat leaks could occur. With use of thermobank, this heat does not occur. The surface of the Earth is characterized by the fact that heat moves through the Earth very slowly. The speed of movement can be set at approximately 1 meter per month. And the ICAGs use this knowledge to be able to store and insulate heat deep in the ground in the summer months, and to use the accumulated energy for heating of roads or runways from the thermobank during winter. So the functionality of solar road system, or SRS. The solar road system has many uses, but it has two main functions. The first one is cooling function, and the second one is heating function. The cooling function is used in summer when the concrete or asphalt is overheated and no longer can absorb additional solar energy. Then this function is used, which does not cool the concrete in the direct way or direct sense with cold water or anything or air, but it helps the concrete to cool down by transferring the accumulated heat through the pipes directly to the thermobank, where heat and energy, the thermal energy, are stored until the winter months. Therefore, the concrete is cooled by removing heat, and the concrete regains capacity to store or absorb additional thermal energy. In the summer months, the obtained solar energy can be used as a power supply for some buildings. For example, airport structures, for example, terminal. And if we are talking about the second function, the heating, as the name implies, it is used in winter months, and the heat stored in the thermobanks is used to heat the road with it. Such heating during the winter months, in the presence of layer of snow, for example, on the runway, can reliably dissolve this layer and ensure that it is safe without the use of sending salts or other techniques. And in the picture, we can see the initial construction of this system, of SRS system. As I said, is a system of pipes incorporated into a layer of, for example, concrete or asphalt, and also it is secured by steel grids. So advantages of the system. The advantages of the system are that it draws energy from a renewable source, so there is no need to consider the possibility of its depletion. The system has no or minimal negative impact on the environment because it uses solar thermal energy obtained from the surrounding environment. Also, minimal service interventions are required to ensure the lifespan of the system, and heat pumps that are used to transport energy from one point to another have the advantage that you can use them in many other ways. Assuming the solar powered pumps are used, their service life is considerably longer than for other pump types. It is also advantageous that in the summer months, when there is an excess of thermal solar energy, it is possible to use the system exclusively to power pumps and other necessary elements of the system. It can also be used to power the systems of adjacent residential complexes, therefore reducing overall costs. And for the winter maintenance of roads or runways, as I said, it's a great way to reduce the snow layer and the formation of ice. So there is no need to use heavy equipment. And the technical failures are minimal of this system. It is, as I said, incorporated in the concrete. So we'll get also to the disadvantages of this system. The SRS can be used and is used in winter maintenance plan when used in a winter maintenance plan. The master of winter maintenance on the airports are able to incorporate the functionalities and functions of the system into the plan for winter maintenance and the reducing overall cost of these operations. For the disadvantages of the system, as I said, it is incorporated in the road structure. So the concrete structures, but especially asphalt surfaces, are prone to temperature changes. And when using a solar road system, care must therefore be taken to ensure that the road and its surface heat up gradually and smoothly. Increased cost of building an area with implemented SRS is a really big problem, because the initial cost of incorporating the system into the whole transport infrastructure, and cement concrete pavement heats. If this concrete pavement heats up too quickly and suddenly, it could suffer a thermal shock, and this could result in cracking of the concrete surface or other types of road defects. The last or the biggest disadvantage of the system is that in the event of fault on the road, its repair will be considerably more difficult. So when we are talking about the utilization in airport construction, the use of this system in airport construction represents a really wide range of possibilities. The biggest benefit would be the system and use of the system in winter months during the winter maintenance of specific airport movement areas, for example, taxiways or runways. Because with the arrival of winter, airports are entering a period when airport staff must be constantly prepared for anything that may happen. A lot of snow is needed to completely close an airport, but thanks to modern chemicals or other heavy machinery that is used to eliminate and to remove the snow and icing from these specific airport movement areas, it keeps the airport running. The highest priority when talking about construction and therefore the maintenance of airport areas is to prevent ice formation at the runways. And usually they use, the staff at the airport use chemicals with special formulations, but they are very expensive. And here comes the SRS, the solar road system, because runways with a solar system incorporated would be an effective solution of how to ensure the smooth and perfect operation of the airport. The airport, as well as its staff, to provide winter maintenance for the airport, must consider the climatic conditions in which the airport is located and provide the means to carry out winter maintenance. So in the picture is a conceptual model of airport with SRS incorporated. As I said, the elimination of ice formation is the most important factor in the efficiency of the system. And also the winter maintenance, its task is to maintain smooth and perfect condition of the runway. So any icing could result in a problem or in closing the runway for necessary operations. The problem with the use of this system could arise in terms of bearing capacity, because there are multiple aircrafts on the taxiways or runways. But as I said, this is like the main focus of one of the main goals of the project, to increase the bearing capacity of the SRS structures in this area, these runways or taxiways. So they incorporate carbon fiber into the upper layer, and that will increase the total bearing capacity of the system. The biggest focus is that the SRS uses clean accumulated energy from renewable sources, and therefore could provide heating also for adjacent airport buildings. Thing that we must consider is geothermal activity, as seen in the picture. This conceptual model works with the concept that we also use geothermal activity, if there is any, in the necessity of the airport, which could help us with accumulating and storing the energy, also the solar energy, the thermal energy absorbed by the surface, which is transported into thermal banks. So the practical application of the system in the terms of airport construction and maintenance is that in the case of winter maintenance of airports, the priority is to ensure the smooth and safe operation of the airport, as I said. And the weather has the biggest impact on the operation of the airport. While the riskiest stage of the flight is takeoff and landing of the aircraft, which is from the runway, therefore the airport staff must ensure smooth condition of the runway. And if any icing forms on the runway, the coefficient of friction is significantly reduced, which means that if pilot starts to brake, it will take longer time to completely stop the aircraft from moving. And the usual procedure assumes that after detecting icing and confirming a reduction in the coefficient of friction, technical staff are sent under the guidance of winter maintenance master to eliminate icing, on the road or on the runway. Another problem is that when braking, the wheel may deviate from the assumed trajectory because it loses traction with the road. And at the large hub airports, special sensors are installed on the runways that monitor the runway surface as well as meteorological conditions. And if the conditions for the formation of icing are met, and if the sensor detects its formation, an alert is immediately sent to the airport coordinator. This is usually the airport dispatching department, but at small regional airports, the monitoring function is performed by so-called meteorological offices. To demonstrate the effectiveness of the system, the airport model with reinstalled runway sensors for icing detection is selected. And here is also a methodology in the form of a flowchart. It is a methodology of elimination of icing phenomena using SRS. If the sensor detects the formation of icing, and alert is sent to the dispatching department. It is reasonable to assume that the coefficient of friction always decreases with the occurrence of icing. Subsequently, the solar road system can be started either automatically, when the system starts automatically after receiving an alarm from the sensor system, or it can also be switched on manually by the person responsible for the operability of the runway. These methods can be configured according to the client requirements. In any case, after switching on the runway heating with incorporated SRS, the icing is eliminated. It is then necessary to check the coefficient of friction again, and if it is sufficient, the track is declared operational, the runway is declared operational. This procedure, when the SRS is incorporated, significantly saves the time required to ensure the smooth conditional operation of the runway. Another significant advantage is the minimized environmental impact of winter maintenance. And when using common chemical agents to eliminate icing on the road, these agents have a negative impact on the environment. When using this system, there is no disturbance and degradation of the runway surface, as in the case when the airport staff is using chemicals. And also, finally, the money spent on the purchase of these chemicals and all the technology, the heavy machinery that is used to ensure and to provide backup for any winter maintenance operation is reduced. And the only problem is to ensure adequate bearing capacity of the track, as I said, but it is the subject of current research, where it is possibility to ensure and to increase the bearing capacity of the track by implementing carbon fibers in the overall structure of the road, which is one of the possibilities. Also, there is possibility to implement nanoparticles, but it is only in the way of current research. There will be needed more research in this area, mainly when we are talking about nanoparticles. So in conclusion, the technological progress is becoming more and more noticeable in everyday life. In order to improve the quality of life, but also to ensure the protection of the environment and its preservation, constant development is needed in area of construction and maintenance of transport infrastructure. The concepts of bi-cities and the ways to achieve this idea are especially at a time when the consequences of climate change are more noticeable than ever before. Therefore, these concepts are more important than in the past. One of the components that would be used to ensure the sustainable development and sustainable environment in the field of transport infrastructure is the presented SRS system. In the field of transport infrastructure, continuous development is needed to meet the specific requirements. And one of the concepts of implementing a SRS system in the transport infrastructure is that the energy collected would not be used only to ecologically ensure winter maintenance or of the airports or any other road systems, or partial supply of electricity to adjacent buildings, but this concept also presents the possibility of connecting the power supply of electric cars directly during their stay on the roads, when the accumulated solar energy and thermal energy would be transmitted directly to the electric cars using special panels on the road surface. This could be ensured by the principle of wireless power supply, similar to the case of wireless charging of mobile phones. But such cross integration between these technologies is still the subject of future research. So that will be all from my side. Thank you for your attention. If you have any questions, feel free to contact me. Thank you.
Hello everyone, my name is Mahmoud Abdullah, and in this presentation, I will demonstrate my work, the role of CNN for intrusion detection systems, and improve the CNN learning approach for SDNs. In my agenda first, I'm talking about the main differences between traditional network and the SDN, and the security challenges in the network, the problem statement, and the different regularization technique to solve the problem of overfitting. Then I am going to talking about the proposed CNN model and the dataset used for training and evaluation. Then I represent the experiment results and the future work. Here in figure 1, which represents the conventional networks, which mostly applied today, we can find many of different devices, router, switches, and all of these devices distributed through the whole network. And in case we already need to implement any policy, quality of service, routing, we need to access each device individually. This is because the control plan and the data plan are integrated in the same device. And this can cause many of the different management problems and error prone as well. To solve all of this problem, the new technology is software-defined network, or SDN, which already physically separated the control plan from data plan. And here we can manage the whole network devices, routers, switches, access point from centralized location, which is SDN controller. Furthermore, we can add or apply any applications like load balancer, quality of service, threat detections and provisioning through the application layer directly. However, the security issue is the main challenges in SDN. In fact, security is double-edged sword. We can use the SDN to enhance the security by adding intrusion detections and the provisioning systems through the API or application layer. And at the same time, the physical separation of control plan and the data plan generated new attacks that not exist before in traditional network. Furthermore, all of attacks that are common in traditional network can occur here in SDN as well, but with severe impact. In traditional network, any attack can only impact on small portions of the network, probably for the same vendor. But here, in case the attacker, for example, able to access or attack the SDN controller, all of the network will be filled down. And here, one of the most popular work for SDN already divided the attack vectors that can occur in SDN into 7 vectors. Some of these attack vectors are common with traditional network, and some of these vectors are new with the new paradigm, like attack vectors number 3, which represents the attacks between in the communication channels between the data plan and the control plan. And the attack vector number 4, which represents the attack against the SDN controller itself. And one of these severe attacks is distributed denial of service attack and distributed denial of severe attack, DOS and DDoS attack. This attack already can impact all of SDN layers with severe impact. Many of different techniques are already used for intrusion detection systems, and one of the significant solutions is using the machine and deep learning techniques. In this work, we already narrowed down our problem by using deep learning techniques. Since the machine learning or classical machine learning techniques inherits many of different problems, because it based on feature engineering and need almost expertise to select the best features for each attack vector. And this cannot be easy task, since the attacks that can be applicable or suitable for one class not necessarily applicable for another attack classes. Furthermore, even some researchers start to deploy deep learning for anomaly detection, but this technique, they have a low ability on the network flow analysis. This is because the network traffic is very dynamic and the data can change over the time, or can lead to the concept drift. The relations between input and the output almost change with the time. And this can lead to the performance of machine learning and deep learning in general can decline over the time, or in different way, not generalize well to the new environments or new data. And another problem in the traditional neural network, this technique inspired by a huge number of training parameters, since the adjacent layers units are fully connected together. And this can limit the size of neural network layers and slow down the training process. Here to solve all of this problem, I'm using the CNN model to reduce the exploitations of the coefficient parameters, and at the same time, I used the regularization technique to overcome the problem of overfitting, and then we enhance the performance of the model for anomaly detection, or in different way to enhance the performance of the model to detect the unseen data or zero-day attacks, or the attacks that never seen before during the training. And because of that, using the regularization. One of the most popular regularization technique is L1, L2 regularizations besides the draw-out method. The main idea behind the L1 and the L2 regularization, we already adding a new term to the loss function. And this term is the absolute value of the magnitude in case of L1 and the squared magnitude in case of L2. Here, this is the loss function. This is the normal. We're adding the new term, which is lambda divided to nm, multiplying with the absolute value of the weight. And this term can be the square value in case of L2. And the main idea here, we already banalize the weight to obtain smaller weights. And the smaller weights, of course, can lead to simpler model. And the simpler model is less for overfitting. We can see here in L1 or L2, the white circles already represent the gradient. And the main idea here to reach the optimal value represented by dot. But we assume the overfitting can occur here. We already prevent the model to reach the optimal value by adding another constraint, which is the L1 space. And this already constraint the weight to reach the optimal value and prevent the overfitting. Another technique used to enhance the performance of the model for regularization is the drop-out method. And the key idea behind the drop-out method is randomly ignore some units from the network with probability during the training. All of these units are used in testing. And the best value of probability is usually between 0.5 and 0.8. This is the model I used. I used two CNN to perform with new attacks that never seen during the training. And I used the L2 regularization since, based on many of the different studies, L2 perform well compared to L1. Since L1 already banalized the unimportant feature and to reach zero. But in L2 already reduce unimportant feature, but never reach to zero. And because of that, it will less for information loss. The model contains two convolutional layers, two maximum pooling layers, and I added the draw-out layer after the second maximum pooling layer, and I used one fully connected layer and the classifier here is the Softimax layer. The input feature, I used the 48 input features and converted this feature into image with a scale of 8/6. The dataset I used for this model is INSDN dataset. And this dataset already generated in 2020 to overcome the problem of availability of datasets for SDN network. And this dataset contains many of different attack vectors, like data to control balance saturation attack, link flooding attack, follow rule flooding attack, password guessing attack, remote application exploitation attacks. Before I applying the model for the input data, further pre-processing steps are used to prepare the data for the input. And this step is using standardization method or Z-score normalization. The idea because the value of the features are different from one feature to another. And if I already applying this directly to the model, it can cause some errors and slow down the process of training. And furthermore, I used the attack and testing phase from different distribution from which already used during the training. This is to test the performance of the model for anomaly detection or for the attacks that never seen before. And this is the value of samples which already used for training and testing respectively. Here, I used the different evaluation matrices to test the performance of the model, like precision, recall, F-score, ROC, area under curve, and accuracy. Here in this table, represented the relation between precision, recall, F-score for the proposed model and the different classical machine learning techniques. We can see here the proposed CNN model performs very well compared to all of different techniques. We can find the naive Bayes and random forest, the worst models, and we can find the KNN followed by deep neural network perform very well after our proposed one. For further evaluation, I used the ROC curve to represent the relation between true positive and the false positive rate. And the area under curve or EUC is the measure of the model capability. We can see here the CNN model or proposed model outperforms all classical machine learning techniques. We can see it with a score 0.98. In contrast, we can find in the naive Bayes and random forest perform very poor with EUC equal to 0.50, 0.5, and 0.56. And this very poor. Another evaluation matrix is the accuracy, and we can see the proposed CNN model gives the highest accuracy compared to all classical machine learning techniques. For the future work, I am going to deploy the proposed model under the SDN context. Further, I will evaluate the network performance, taking into account throughput, resource utilization, time delay, and requirements. Thank you very much.
Hello, my name is Ivan Šimunić. My colleague Ivan Grgurević and I come from the Faculty of Transport and Traffic Sciences. For this year's Fabulous conference, we did a case study of network device configuration automation using the zero-touch provisioning model. The presentation begins with defining the purpose and aim of this paper. To begin with, some challenges of traditional networks will be presented, and thus the challenges of implementing network devices in the network. This is followed by an overview of zero-touch provisioning model, the environment developed for this testing, and finally an overview of the results. So the purpose of this study is through the process of ZTP model implementation in an environment founded on existing solution to present all the benefits the application of which would significantly reduce the network installation time for the network experts in the production environment, reduce the financial cost and the likelihood of human error. The aim of the case study is to automate the configuration process of Cisco IOS XC network device when implementing the device into the network according to the ZTP model. The device automation will be based on downloading the configuration script from the appropriate server, which will then be executed on the device and with the help of the configuration file also located on a certain server, perform the configuration. Today's networks support a very different IT environment compared to just a few years ago. There has been a significant rise in the use of client devices, increased adoption of cloud-based applications, and the increased deployment and use of the Internet of Things in the network environment. In the past, one IT worker might have supported 200 devices. Now, one IT worker may have to support maybe 100,000 of devices. Over the years, the networking technologies that have been the foundation of interconnectivity between clients, devices, and applications have remained fairly static. While today's IT teams have a number of technology choices to design and operate their networks, there hasn't been a comprehensive turnkey solution to address today's rapidly evolving enterprise needs around mobility, IoT, cloud, and security. The network must change to support this new normal. It has to behave as a cohesive, intelligent system that generates network data and using automation and analytics to solve security and operational challenges. To gain a better perspective, let's take a look at network operations. It basically breaks down into three buckets. The first one is day zero operations, which implies new device installation. After that, day one operation starts, which implies initial configuration of network device, and finally day two operations, which implies management and optimization of current network infrastructure. Day zero and day one operations are one-off operations versus day two operations, which are ongoing throughout the life cycle of the network infrastructure. The traditional network operation model is characterized by inflexible software where it's tightly coupled with the hardware. There is little room for customization. The configuration is performed using CLI with limited automation capabilities. Research like the one from Cisco suggests that day zero automation can reduce implementation costs by as much as up to 79%. Also, due to the lower probability of configuration failure, it is possible to reduce the time spent in finding the problem by 50%. Besides, 70% of all network errors and 35% of all total time during which the network was not functional were caused by human inconsistency in configuration, which could be significantly reduced by introducing automation models for the implementation of network devices. ZTP provides open bootstrap interfaces to automate network device provisioning in heterogeneous network environments. The holistic approach to the definition of the ZTP model suggests that network devices that are connected to the network should be configured automatically. In more detail, ZTP could be described as the automation solution developed in order to reduce the probability of the occurrence of error and time saving for the network experts in the implementation of the new network infrastructure. The ZTP model makes it possible for the network device to be automatically provisioned by obtaining the necessary information from the network, eliminating most of human interventions. So far, network devices have been configured in such a way that the network expert first downloads the appropriate version of the OS, performs the initial configuration, connects the network device, after which remote configuration is enabled. In the case of ZTP model, the device only needs to be connected to the network and started. The device then communicates with the DHCP server, wherein DHCP will provide the device with the pre-configured option 150, which provides the address of TFTP or HTTP server, and option 67, which provides the file path to the files on the TFTP or HTTP server. With this information, the device can access the TFTP or HTTP servers and download the Python script, which will then be executed on the device and apply appropriate configuration. The process of developing the environment in which the case study will be presented requires a two-step approach. First, it will be necessary to define the network topology in which the ZTP process will be performed and to configure the network device and servers on it. Second, the development of the script in the Python programming language will be executed on a Cisco Cloud Services router. This is followed by starting the device and applying the configuration. Of course, it is necessary to use a device that has ZTP functionality. We used a Cisco device with iOS XE operating system that comes with various programmable interfaces in this example. Inside the device there is an IOX framework that provides hosting capabilities to various applications. Thus, within this framework is Guest Shell. Guest Shell is a virtualized Linux-based environment developed with the purpose of running custom Linux applications, including Python for automated control and management of Cisco devices. Using the Guest Shell environment, it is possible to install, upgrade, and manage third-party applications. It is primarily intended for certain device management tools and applications. When running the ZTP process, IOX is first enabled, which manages various applications, including the Guest Shell environment. Guest Shell uses a virtual port group as the source interface to connect to the outside network through network address translations. For the purpose of testing the ZTP process, we also create a Python script. The script imports 3 Python modules, and these are RE, CLI, and JSON module. Module RE or regular expressions represent a string of characters which create a pattern to search a particular string. Then CLI module, which, as already mentioned, is used for passing comments to the network device from the Python environment. The script defines 3 functions for every step of the device configuration, which are called at the end of the script. The first function, getSerials, has the task to use RE module to parse the serial number of the network device that is obtained on it by submitting an adequate command via CLI module. This function eventually returns the variable which contains the requested serial number. Furthermore, the function getConfig has been defined for the purpose of downloading a configuration file in JSON format from a HTTP server. A unique URL is the first defined, which is then passed along with the rest of corresponding file download command via the CLI module. After the download, the JSON form is converted in a dictionary data, in the list of dictionary data, which is then returned by the function. Finally, the function configureDevice has been defined, which retrieves the corresponding values of variables from the list of dictionaries and passes them throughout the CLI device configuration module. The configuration in this case is for the purpose of displaying the ZTP model, and the arbitrary commands are selected. The configuration file would be written in easy-to-understand JavaScript object notation, or JSON, format, where the values could be entered by anyone and not just the developer. In this way, it is possible to configure a large number of devices in a very efficient way. So in this file, it's possible to see the serial number based on which the script recognizes which configuration to choose, then the IP address, network mask, and password to access the device. The ZTP model will be tested in emulated network by using the Emulated Virtual Environment Next Generation, or EVE-NG. A very simple topology with the necessary devices and services was chosen for the test environment itself. Thus, router 1, switch 1, Linux server, and Cisco Cloud Services router on which the ZTP model is tested are connected to the local network. Thus, via router it is possible to access the internet to download TFTP service to a Linux machine on which the script and JSON file are stored. Also, a DHCP server was set up on the Linux machine for option 67 and option 150. After configuring the network environment and uploading the script and configuration file to the service, it is possible to connect the router with ZTP functionality to the network and run it. The device receives the necessary information, downloads the running script, and configures the device. The display of the script execution results can be seen on the next slide. First screenshot shows the hostname configuration on the device. Further, in the same display, it is possible to see encrypted configured password which is used to enter the privileged exec level. Finally, there is a display of configured domain name for the purpose of allowing access via the SSH protocol. The hostname and the password values were parsed from the JSON file. The next screenshot shows the configuration of the virtual port group interface, whose configuration is automated when enabling the guest shell environment. In addition, the script configures the Gigabit Ethernet 1 interface, to which an IP address is associated, which is parsed from JSON file. The next screenshot shows the configuration of IOX application framework. The configuration of the IOX framework is followed by the configuration of NAT, where the role of the inside interface is played by the virtual port group and the outside interface by Gigabit Ethernet 1. NAT is configured automatically when enabling the guest shell environment. Finally, the last picture shows the configuration of the console port and the configuration of virtual terminal lines, thus enabling remote access by means of the SSH protocol. Although there are various variations of implementing this model, the case study in this paper presents the possibility of use in broadband access on the example of Cisco router with iOS XE operating system. The realization of the ZTP process is emulated in the emulated network has confirmed the assumption about its efficiency. Although ZTP automates the most part of the configuration process of new devices in the network, its execution requires certain preparation. In example, starting of the necessary servers, creation of the script and configuration file, and certain tests. Such a model has special advantage in somewhat larger network implementation, where the saving of the time, costs, and reduced probability of error especially comes to the fore. Discussing the ZTP model, it should be emphasized that all the major network equipment manufacturers are oriented to device configuration automation, but the way of implementing the ZTP model differs somewhat from manufacturer to manufacturer. Therefore, the implementation of the ZTP model in various network scenarios and heterogeneous network with several different manufacturers will be a little less efficient. In order to solve this problem, it will be necessary to perform additional research and develop an appropriate type of joint platform and the necessary components that will allow the performance of the ZTP model in the networks with devices from several manufacturers. Thank you for your attention.
Good afternoon, everyone. I want to thank you for coming here to see our presentation of the effectiveness of remote wipe on smartphones. My name is Kevin Jochums, along with my fellow researchers, Andreas Bello and Raymond Cho. We're here from the University of Texas, San Antonio. Our presentation will consist of looking at the objectives that led us to our question for our research, the information that we found during our research, the methodology we used, examining the results that we found, the conclusion, and some ideas that we think on things that should happen in the future. To begin with, we all know that what data we can recover depends on which specialized tools or forensics tools we use and how the data was actually deleted. The smartphones actually allow us to reset the phone back into factory condition with internal software. But the problem that we see is this phone is easily moved, easily transported, which means it's also easily lost. People have recognized this and now allow us the ability to do a remote wipe of the data that's on that smartphone. But we have to ask ourselves, can we recover the data and how much of it can be recovered after a remote wipe of a smartphone? So we started off by looking at smartphones. They're outselling computers and laptops at a high rate. Because they're being easily carried around now, that means a lot of highly sensitive PII is being carried in somebody's pocket, in their car, or laying on their desk. On average, users update or change out their phones every 2 years. This could be due to a newer model, a broken phone, or a stolen phone. There's 2 ways we know of deleting information. We can delete the headers or do a secure deletion, which is an actual wipe of the data, making it impossible to recover. Within a smartphone, there's 3 ways of deleting your data. You can manually delete it. You can go in and get rid of your username, accounts, any particular extra apps that you've added, pictures. You can use the factory reset to put the phone back in the same condition or wiped out condition that it was when you initially got it. Or you can use what they're doing now, which is a remote reset. There's a problem when you're dealing with smartphones versus dealing with a computer or flash drive and how it stores memory and the type of memory it uses. When you're dealing with a computer or flash drive, you have the ability to erase and write on the fly bit by bit. That is not the same within a smartphone. Smartphone uses NAND flash memory, which actually uses blocks of storage or cells of storage. You can mark information within those cells to be deleted, but until every bit that's within that cell is marked for deletion, nothing in it gets deleted. Plus, once that cell is full, you cannot write in that cell until everything's deleted. So there's special software or processes it uses to look for those individual bits of memory that's still being used. It moves it to another cell, making it so it can wipe out that whole cell. Then you can start writing it again. What this means is there's a lot of data still left in these cells that can possibly be recovered. Where you recover it, software, hardware, or else what we've been able to talk about now and see is chip-off technologies, where they will actually solder wires onto the actual chips to remove the data bit by bit. When we talk about software, you have proprietary software based on the operating system of the device you're using to recover, such as a laptop, you have Windows or Linux. The toolkits, plus the software is also depending on the phone which you have. Are you dealing with an Apple phone, an Android phone, or a Windows phone, or other? Toolkits is hardware. You see these in your phone stores when you want to transfer data from one phone to another, or if you've broken your screen, it allows you to extract the data within the phone. Encryption of phones is an option to hide your data, but when this particular type of technology, only the encryption key we're seeing based on our research is deleted, not the data that's on the phone. When it comes to remote wiping, there are 3 ways to access the phone for remote wiping. Based off the operating system of your smartphone, such as Android, you can go to the Google website. If you have an iPhone, you can go to the Apple website. There's also the ability going to the phone manufacturer's website, such as a Samsung phone. You can go to the Samsung website and it allows you to remote delete. or else there are third-party websites that are developing, mostly within the anti-malware and antivirus websites, such as Norton's, which allows you to do remote wipe or remote deletion of your phones for security purposes. Now, your remote wiping relies on the ability of you to connect up or talk to your smartphone either through Wi-Fi or cellular. You go to one of the websites that we mentioned above, and then you're going to do secure authentication protocols into it. Once that's done, it sends a signal to the phone. The phone then starts its wiping process. Usually when it's done, it's going to send a message back saying that it's done. Now, there are a couple issues with this. One is, what if you can't connect to your device? Well, these websites will continue to send out a signal to your device until such time as that device is turned on, brought online, accesses cellular or Wi-Fi, and then it'll start the remote wipe. The other way is the amount of time it takes to actually perform the wipe can be anywhere from 30 seconds to 5 to 10 minutes on average and up, based on the type of wipe you want to do. You have the ability in most cases to back up the data on that device remotely and then wipe it. You have the ability to just back up the data on that device. Let's say your screen's broke and you want to be able to get the information off of it yourself, or you can wipe the data. Now, in all of our research, we found there was a lot of work done on data recovery after a factory reset, going all the way back to when smartphones basically were starting out. There's very limited academic literature regarding the effectiveness of data recovery after a remote wipe. That leads us into our paper. So the methodology we chose, we used the mobile forensics investigation model of preservation of data, acquisition of data, examine our findings, and then look at the reporting of our data. So we started off by selecting our equipment, what we were going to use, what type of wiping methods, what type of recovery tools were we going to use to pull the data back. We know we had to establish a baseline. We had to test the effectiveness of our data wipes and test the effectiveness of our data recoveries. We had to have repeatability of all these tests, and we wanted the ability to repeat these tests if we wanted to add a slight variation into it. We also wanted to be able to analyze our data in the end. So to begin with, we chose 3 smartphones. We chose these phones based on the fact of availability, still in use, and that they were beyond what we found in research where there was faultiness to their factory resets or their encryption technology, such as the iOS 4 and prior. You can still get minimal to maximum recovery of data. And Androids, the operating systems 2.3 to 7.0, you can get minor to almost full recovery of all deleted data. This also varies greatly depending on the manufacturer of the phone itself. Here we had version 6.0, which is near the better end, and the Samsung 6.0 seemed to have a good factory reset built into it based on research. And the iPhone 6 had version 13.2 in it. The 2 software recovery tools we had was Mobile Edit Forensics Express by Compulsion Labs and Mobile Phone Examiner by Access Data. Now, MPE has been used by a lot of different people to recover data when you've done normal deletions on your phone. They also have a licensed version, which is more intensive to get back into a bit-by-bit recovery. Mobile Edit, we were actually able to talk with the owners of it, and they granted us a 60-day license into full access of this particular software, which was great. So this is one of the more higher end that's used in police forensics and international forensics now. We found 3 ways of deleting that we were going to use: a third-party app to wipe out the unallocated data. We were going to use a factory reset, and we're going to use the remote reset. Now, we did find that the G900, we had to set up an actual Samsung account online because the Google did not recognize this with the remote wiping ability. The G70 phone, Android, we were able to use the Google account, and with the iPhone, we were able to use an iCloud account. So we began by creating our baseline. Since these phones were collected up by different people, there's personal information that's still on here. We did not want to accidentally leak this information, and because they were owned by different people, we wanted to make sure that all the phones had basically the same information on it. So we began by wiping out all of their PII, their accounts and passwords. We then created online accounts for both data recovery, data backup, and remote recovery, or remote wipe of these phones. We selected a bunch of pictures, emails, SMS, websites that we wanted to access with these phones, and we actually had a calendar with events on it. We applied all of these to all three of the phones. When we were done, we applied a few extra apps that were common to most people, and then we proceeded to update the phones and the apps. Once everything was completely updated in that, we installed 2 additional apps on the Android phones, which were wiping apps, Shred-it and Secure Wipe. We selected these based on write-ups from different forensic reports on their recommendations and the effectiveness that was supposed to be between these 2 particular apps. Unfortunately, when we did this paper and the research, there was no available third-party apps for wiping within the Apple Store. So these were only added to the Android phones. Once everything was up and we were done installing all the information and wiping out what we needed to wipe out, we backed up all the phones to our online accounts. That way we can recover the data when we wanted. We were also had the ability, based on the mobile edit software, of creating a bit-by-bit backup of these particular phones on our computers. Now, note, we had the ability to, we could have rooted a phone, we could have encrypted a phone, we could have screen locked the phones. We did not do this for this test and experimentations. There were several reasons for this. The biggest one was, even though we had the ability to crack through these particular security layers, we were not able to, in our minds, get repeatability once we actually broke into the phone. So we can repeat these tests over and over in case something happened or a glitch happened in it. So the test structure was set up. As you can see on the left, here's an example of a screen from Mobile Edit on the top one. We could actually pull a full content data recovery. We can concentrate strictly only on the deleted data, strictly only on the device information, strictly on analysis of applications. There was also hidden screens, which allowed us to both crack into a phone if it's screen locked, or if it happened to be blocked from anybody getting into it. And I'll get into that in a moment, which is the next point. We found that when we got into the Androids, unless they were placed into the debugging mode, we were not able to extract the data that we wanted or see the data that we wanted. Now, we could have rooted the phones using the Mobile Edit software, but basically that destroys the ability of using that phone. We've rooted it out. But we were able to turn on and turn off the debugging mode. So we added an additional set of tests for each of the Android phones, where we ran all the tests both in the debug mode and the non-debug mode. You can see some of the results and the differences in the files that we found. The next thing we did is we conducted a delete data only test on all our phones. Even though the full content backup or extraction showed us all the files that were listed as deleted or were deleted on the phone, and we recovered them, we wanted to have the ability to dig down in and focus strictly on also the deleted data to see if there was a difference in what was recovered. The next step was to use and apply our third-party wiping apps on the unallocated memory space. After each of the apps were run, we performed a deleted data only test. This should have given us a difference after each of the wiping apps. From there, we did a factory reset. Once we did a factory reset, we repeated steps 1 and 2. We did this without an account activation. The reason for this is, once we turned on the wireless and we connected up to the internet and we loaded up an account in there, we actually changed the phone because it could start updating and upgrading the software and also backing up the data in a recovery mode. We did not want it. We wanted to see exactly what was left after the factory reset. Now, we did have to actually install the accounts when we went to restore the phones from our online accounts. At this step, we also did repeat of account steps 1 and 2, so we can compare our baseline to our backups. The next thing we did was perform our remote deletion. Once again, we gathered information from both our full content and our deleted content. When we got down, after all of this and several days worth of work, we analyzed all of our data. Now, some of the things that we did find initially, our MPE tool, even though we had a license for it at the school, it had several issues with it. One, it required administrative rights. When you're working on somebody else's network, they really don't want to give you administrative rights to the computer. We did fight through that, and then we found out that the license was outdated. So we weren't able to actually use this software, and we were not able to get the budgetary process in time to get the licenses updated. So all of our tests ended up being done by the mobile edit software only. As we talked about earlier, the Androids required either being rooted or debugged. We decided that we would just turn on and off the debugging mode, since it was a simple switch and allowed us to have repeatability versus actually rooting it and messing up the internal software. One thing that we did find, which was very interesting, is when we actually looked at the data after the third-party app wiping software. If you look down in the bottom of this slide, when we did our data recovery after our initial baseline, we found that there were 10 downloaded files. Now, we also were able to identify 8 additional files that were deleted. In fact, our reports listed exactly like this. They were in red, deleted, and showed us what the file names were. When we performed a deleted only test, same 8 files were found. Unfortunately, after we performed the third-party wiping with the shredded and the secure wipe, we were still able to see those 8 deleted files and recover it. We believe that this has to do with the NAND memory technology that's in there and the way that smartphones store their data. We weren't able to actually move the data, which left blocks that were still open that had some deleted data within it. The next thing we did is we actually looked at the percentage of data that was recovered, the percentage of particular files that were recovered, also the percentage of different files that were restored. As you look down the list, you'll see the words baseline versus restored. Is when we restored it back to its condition after restoring from online backup. Baseline versus remote, which is our baseline versus our remote wipe, how much data was there. Of interesting note was lines 1 and 3. Our changes after our factory reset and changes after our remote wipe. 52% of the data was removed. 41 to 52% actually within our Androids. Over 84% of the data was removed from our Apple phones. We did notice, which was interesting, line number 2, change after restore. We found that even after we did our restore from our online accounts, 30% of our data was still missing, 11% out of the G900 and 10% of the data from the iPhones. This is something to examine further on, that you're supposed to be able to put your information online and restore it completely, but obviously it's not happening. Since it wasn't part of our research, we went on. We did examine all the files that we were able to recover. We examined the files that were versus the files that were deleted, and we found that in the end, both the factory reset and the remote wipe, the PII data was sanitized from these phones. Now, this is the brief recap of the data that we were able to recover. These are the 3 different phones. The biggest thing of note is down in the bottom. You'll notice that in the first phone, there was over 4,200 files on the phone. After the factory reset, there was only 2,000. We were able to recover 900 files when we restored it from online. At the remote delete, put it back at the same 2,000 files. The same files, except for a couple, were there after the factory reset and the remote, which showed us that both worked just as effectively and removed the same files. When we get over to the Apple, you'll notice that we went from 6,000 to 1,000. It deleted a lot of information off of the Apple, recovered back up, and deleted back down to the same 1,000 files. Overall, what we found is, on our literary review, the older versions had issues with their factory reset. Older versions of smartphones had issues with their factory reset. They were faulty. The phones also lacked encryptions, though that had encryptions didn't have it on by default. Using third-party wiping apps that we found, it seems to be, as of this date, there's still some issues with using NAND memory. The factory reset and the remote resets, based on our tests, were effective in wiping out the PII. But we do look at some items in the way ahead. Continued research should be done with newer model smartphones and other recovery software. We should have further examination of third-party wiping apps with NAND memory. We need to have deeper software analysis, maybe of the files that remains, the SQL and the XML files for bit by bit, if there's anything within it. They were reduced down to 1 kilobyte only. And we should have some more data research on the recovery of a deleted encryption key, although MobileEdit has been able to do this in most cases. So if you were here, I would ask you some questions, but since you're not here, I'm going to leave you with this slide. You're welcome to sit there and contact us if you want copies of our data or copies of our information. We thank you.
Ladies and gentlemen, my name is Tomáš Mandičak. I come from Slovakia, from Technical University of Košice. I would like to present our contribution with title Evolution Methods of Investments to Mobile Applications and Smart Technology in Construction Projects. Co-authors of this paper are Peter Mesáros, Anna Maria Behunova, Marcel Behun, Matúš Tkáč. The article presents partial research results of Project KEGA, M-learning tool for intelligent modeling of site structure parameters in a mixed reality environment. The presentation is divided to the 4 parts. There are sustainability in construction, next smart technology and mobile applications in construction projects, next evolution methods of investments in construction projects, and last one, conclusion. Sustainability is a new, not only phenomenon, but above all a real need of the 21st century. The emphasis on sustainability is felt every day. Extensive discussions within Europe or world leaders address the issue of environmental burdens and their impact on countries' economies. There is a great deal of pressure on environmentally friendly materials in every sector. Construction is the same situation. There is also pressure to reduce emissions, carbon footprints, or other negative impacts of the industry in the construction segment. Construction is a segment that is largely considered a major producer of waste. As a part of the green policy, several initiatives have been taken to reduce the volume of negative effects in the sector as well. It is necessary to say that the construction sector is closely linked to other sectors. Consumption of materials largely requires addressing the issue of their production. This segment is also demanding on logistic processes. The implementation of a construction project requires great knowledge in the field or logistics. The challenge in this digital age is to reduce these negative impacts in construction with smart solutions and smart technologies. It is the use of smart technologies that can significantly contribute to the sustainability of this segment. Information and communication technologies are one of the tools that can have a positive impact on sustainability and the environment, but also on economic sustainability. For this reason, it is essential to discuss the cost of the whole life cycle of construction project. Progressive technology represents the new possibilities in construction, which on the other hand, improve the digital skills of managers. At the same time, the use of smart technologies in construction brings an increase in the quality of outputs in the segment. Smart solutions in construction and design should lead to a reduction in environmental burdens and a sustainable economy. These technologies can effectively reduce cost and, on the other hand, contribute to better project management. Investment in construction is the second largest amount of investment in the national economy. Investment in IT solutions represent the largest volume of investments. It follows from these facts that the scale of investments in these areas is so large that it is necessary to assess these investments. Therefore, there is a basic research question on how to evaluate investments in smart technology in construction projects. According to several studies, smart technologies implemented in construction are beneficial. These studies highlighted the benefits of implementing digital and knowledge technologies from multiple perspectives. In the context of smart technologies and the use of urban planning, several technologies are useful for solving smart cities. One large group, therefore, consists of the so-called GIS technology and digital technology used for urban planning, proposes intelligent solutions in construction, and also for the city have the ability to capture real-time data that is communicated between stakeholders to optimize decision making by using digital technology. Geographic information systems and digital technologies are based on spatial and temporal analysis of data collected into groups according to their purpose. Their goal is to model future trends and predict impacts on project implementation and environment. These technologies are also largely based on the use of mobile devices and applications that interact. The growth of smartphones is significant as according to the study, the use of smartphones has increased by 2% in the last year. In absolute terms, this currently represents just over 5 billion users. The technology of terrestrial laser scanning, which you see on the picture, and aerial photogrammetry using drones currently represents another opportunity to implement digital technologies and smart solutions in urban planning and construction. It can serve as an effective and progressive tool in the field of 3D spatial digitalization of buildings and their geometric dimensions. These technologies try to display 3D bipod clinks in detail and digital environment, which is to be made for project documentation. This technology automates this otherwise demanding process. The advantage is the simulation of changes itself and simple changes in planning, as it is a digital output. Laser scanners are beneficial to measure buildings and urban areas, including all buildings. These buildings or this construction project is Faculty of Civil Engineering and Technical University in Košice, and the case study where was a comparison 3D scanner and combination with scanning with drones. The fact that it works and that such a smart solution can be applied in practice is confirmed by another study carried out in the city of Košice. The picture shows the building of the Faculty of Civil Engineering, which was the reference for the given research. This building was monitored and had to be turned into project documentation and digital model. For this purpose, three variants of data acquisitions and collection and creation of a digital point model were used. As the picture describes, one of the solutions was to obtain data via 3D scanner. Another variation was photogrammetry, and the third combination were the use of drones. The next picture describes in more detail the capture of the roof and problematic buildings. For this purposes, augmented reality and vehicles appears to be the best solution for data collection. The study compared the sustainability of various methods. The output of this is a fully digital model which can be worked with several programs. Importantly, this model is an input for other technologies, especially beam technologies, which in interaction with geographic information systems and other mobile applications, it can be an effective tool for smart solutions. Evolutions of investment projects is a basic decision-making tool for project managers who are responsible for the success of projects. This also applies to the construction industry, where the volume and scope of investments are among the largest in the country's economies. The implementation of smart and progressive technologies requires the same amount of attention focused on investments evolution, the assessment of different projects, and the selection of the optimal one can be done based on several perspectives. Dynamic methods of evaluating investment projects seems much more used and more appropriate. These include the best known net profile value (NPV), as it is only rarely in the case of investment decisions that the expenditure incurred at the beginning of the investment is used once. If there are greater capital expenditures, which is a fact for the vast majority of investment projects, it is necessary to update capital expenditures through the life cycle or construction project or intelligent so-called smart solutions. The profitability index is related to the net present value of the investment projects. It's a relative indicator that expresses the ratio of expected discounted cash receipts from the project to initial capital expenditures. Other authors have a different view on the calculation and comparison of investments. Previous methods took into account the pre-selected interest rate. The internal rate of return method looks for a percentage equal to the interest rate at which the project is profitable. An enterprise should accept a project if its internal rate of return is higher than the discount rate. Another suitable method is economic value added. This represents the net return on the company's operating activities less the cost of capital. To quantify the economic added value during the entire life of the investment project, it is necessary to convert all individual values and discount and add them. In the case of a positive outcome, the investment brings the benefits of implementing a smart solution. These basic investment methods have their advantages and disadvantages. It's not possible to determine at a flat rate which is the best method. It depends on several factors, and the main criteria for evaluating the investment project. Dynamic methods take into account the time factor, which in many cases will be a better alternative than static ones. For example, for dynamic methods, it's a net present value method, the profitability index, the internal rate of return method, and economic value added. For example, for static method, it's the average rate of return or payback method. And the last one, for example, cost method, it's annual average cost or the discounted cost method. When considering solutions where the main criterion will be cost, it is appropriate to use cost method. An overview of the methods and main evaluation criteria is given, and as you can see in this table. Construction is a sector where there is a large volume of investment projects. In the field of IT implementation, for example, smart solutions, progressive and digital technologies require an axial evaluation based on selected criteria. Smart solutions should bring several benefits that users or investor can define. Based on these, the main criteria are chosen to assess the benefits of the solution. Methods of evaluating investment projects take into account several factors. Most often, it's about time, cost, and which are the key performance indicators of all projects. Based on this, it's necessary to choose the right method of comparing investment plans. This survey points out possible method in the selection of the investment plan and summarized their advantages, respectively the possibilities when it is appropriate to use these methods. At the same time, the paper also provides an overview of smart solution and mobile solution when it is appropriate to use one of the mentioned methods. These traditional economic methods of evaluation are in many cases general, but their use must be based on specific factors. Therefore, it's necessary to consider a specific investment project in new technology, analyze the benefits, and define the main factor based on which they will be evaluated. This research needs to be taken further. This means trying to look for dependencies and creating a methodological model when it is appropriate to use which method. Thank you very much for your attention. And if you have any questions, do not hesitate and contact us for these email contacts. Thank you again.
Hello, my name is George Grispos and I'm from the University of Nebraska, Omaha. This presentation presents the findings from a paper entitled Investigating Protected Health Information Leakage from Android Medical Applications. And this was a piece of research that was conducted with collaborators at Sam Houston State University and the University of Texas at San Antonio. So there are two main motivators that guided this research. The first is the increasing popularity of medical devices connected to the internet. Studies by the European Commission and IBM estimate that within the next decade, over 50 billion medical devices will be internet capable. Separately, a study by PwC estimates that as many as 49% of individuals now own a wearable medical device connected to the internet. And they usually use this to monitor their health, medical, or dietary practices. These devices potentially produce and collect vast amounts of medical and patient information. For example, an internet-enabled next-generation ventilator is expected to generate about 305 data parameters per second, and this introduces all sorts of security and privacy challenges. The second big motivator for this research is that many medical devices interface to a smartphone application. This application usually allows a user to track personal and medical information and any other communication with the medical device. However, previous research demonstrates that smartphones and their accompanying applications can contain user-related residual data. And from the perspective of a medical device, the research indicates that smartphone residual data could be used to identify metadata specific to patients and their interactions with specific medical devices. In fact, further complicating matters, research has established that residual data artifacts generated by smartphone applications can actually be used to identify broad user behavioral patterns. So based on this previous information, this research hypothesized that Android medical applications or apps which have interacted with medical devices are putting user data at risk from a HIPAA security and privacy perspective. Therefore, the contributions of this paper is twofold. The findings support the idea that Android smartphone medical apps which interact with medical devices collect and store residual data that potentially violate HIPAA security and privacy regulations. The findings also contribute to the documentation of forensic artifacts recovered from specific medical smartphone apps. So in order to investigate the hypothesis, we designed an experiment that consists of 5 stages. The first was to set up an Android smartphone and install the Android medical apps. 2, create test profiles on these medical applications and then synchronize the apps with the medical devices. Step 3, actually use the medical apps and their associated medical devices. Step 4, process the smartphone device using a mobile forensic toolkit to create forensic images. And then finally, 5, examine the resulting forensic image in order to recover artifacts related to the medical apps. So the medical devices we chose to include in this experiment were from 2 manufacturers, iHealth and Nokia, and includes a variety of different types of devices, including scales, blood pressure monitors, oximeters, and glucose monitoring systems. So we wanted to have a little bit of a variety with regarding to different type of IoT medical devices. In addition, we evaluated 3 apps that work with these various devices. So we evaluated iHealth My Vitals version 3.7.1 and iHealth GlucoSmart 4.5.3. And then with regard to the Nokia devices, they use an app called WeThings HealthMate, and that was version 3.5.4. So as you can see, when looking in the table, the My Vitals was used for the core scale, the field blood pressure monitor, and the air pulse oximeter, while the glucose monitoring system used the iHealth GlucoSmart, and then finally HealthMate was used for the cardio scale and the BPM Plus. So the initial setup involved the smartphone device being reset to restore the device to its factory settings, after which the smartphone was powered on and the initial setup was completed using the smartphone. The smartphone was then connected to the internet through a wireless connection, and the Google Play App Store was used to download and install the 3 applications. The apps were then executed and test profiles were created. The app's GUI was then used to pair the smartphones with the medical devices. What do we mean by that? In order to allow the smartphone to be able to send and receive data between it and the different devices, a pairing stage was needed. And that basically is selecting the device, enabling a Bluetooth connection between them, and then finally the pairing would actually be initiated. Each device was then used with their respective app once a day for 5 days. In the case of the iHealth glucuring system, which actually measures sugar within someone's blood, for the sake of the experiment, we used diluted sugared water that was used instead of blood to measure glucose levels. So effectively, this is a lab environment. We didn't really care about what the actual substance was going in. What we were more interested in is the information that's being recorded. So for the sake of the experiment, we chose to use sugared water as opposed to blood. In addition to the measurements, as you can see on the screen, that were recorded for each of the devices, we also recorded the date and time of each recording. So we recorded this information in addition to the date and time for each recording. So after the 5-day period, a forensic image of the smartphone's internal memory was created using a mobile forensic toolkit called MSAB XRY. And this is a mobile forensic toolkit that's used widely in the mobile forensic community. The forensic image that was then extracted was then examined using an accompanying piece of software called Examine, version 3.2. And that basically involved loading up the forensic image that was produced, analyzing the image and identifying and extracting artifacts and files related to the medical device applications. So we just focused on the files and artifacts that were related to the applications and ignored all other artifacts. In addition, the analysis also involved extracting certain files and artifacts from Examine and looking at them further using FTK version 6.3 in order to do so further decoding or deeper analysis using a traditional forensic toolkit. So at a high level, the analysis of the forensic images revealed a variety of artifacts related to the smartphone apps can be recovered from the 3 original apps that accompany the medical devices. These include the device readings and timestamp information, device information including MAC addresses, firmware versions, and model numbers. So the second point there would be of very high interest to, let's say, other to attackers who are trying to gather intelligence to maybe launch other types of attacks, like potentially a denial of service attack. We were able to recover usernames and passwords from some of the applications in plain text, a list of devices which have successfully been accessed using a specific account. We were able to recover that information, and also the number of times an account's been used to access a specific medical device. So we could find out this user's using this device X number of times, and this user's also using another device Y number of times. And again, this could be useful to someone who's trying to build a profile of an individual on their medical habits or potentially their medical records. So from a HIPAA perspective, if we look at the results from a HIPAA security and privacy perspective, we can see that 2 out of the 3 apps are potentially putting a patient's data at risk. So in terms of the HIPAA potentials, where we have an individual's past, present, or future physical, mental health condition, provision of healthcare to an individual, past, present, or future payment for healthcare, patient's name, address, patient's social security number, and patient's date of birth. We can see that 2 out of the 3 apps are potentially putting a patient's information at risk from both a security and privacy perspective. So we can see that the My Vitals application is putting both past, present physical health condition, as well as the provision of healthcare to an individual. We could recover that information, as well as the patient's name, address, and date of birth. Likewise, HealthMate, we could recover the first and second points from the HIPAA regulations, as well as the patient's name and the patient's date of birth. However, you can see from the perspective of which is more secure from a HIPAA security and privacy perspective, we can see that the Glucose Smart was the only application where we could only recover the patient's name. So from the perspective of a security and privacy perspective, 2 out of the 3 apps are potentially putting the patient's data at risk. So in summary, the examination of the data supports the hypothesis that medical device apps, which interact with medical devices, violate the security and privacy rules within HIPAA. And this statement holds true for 2 out of the 3 apps evaluated in the research. The experimental findings also reveal that patient-specific information could be retrieved from the applications, including the patient's name, date of birth, gender, as well as weight and height information. In addition to patient information, data related to the patient's use of the device can also be recovered from the medical device apps. And that was relevant, that was what we could see through, we could recover the specific readings from the different types of apps, the different types of devices. So we were able to recover scale readings, we were able to recover blood pressure monitor readings, we were able to recover glucose readings. So the findings from the research have demonstrated how certain apps which interact with medical devices can violate specific security and privacy rules within HIPAA. And actually this information which can be recovered from the apps not only includes personal details, but also recordings and readings from specific medical devices. And this information could actually be exploited to gather intelligence about an individual's medical history. So it could help build a medical profile of someone based on who they are, their date of birth, and their readings. This could be not only used by malicious attacker, but could be used by companies for targeted marketing, or could be used by insurance companies in the future to deny someone medical coverage by saying, well, we find out that you've got X number of readings of high blood pressure over the last 30 days and you haven't told anyone about this. So we're excluding you from future coverage. But it could also be used to, this information could also be used from the perspective of coming up with a detailed pattern of user behavior. So we know if someone has a particular condition or what type of apps that they're using based on the data that we can recover from these specific Android applications. So future work can examine several key areas. We can extend the associated apps and look at other operating systems. We can include diverse apps and their accompanying smartphone applications. So look at other medical IoT devices and their applications as well. We can also look at apps from the perspective of iOS apps and see, do we get similar results from an Apple perspective as we did with the Android devices or the Android applications. Research also needs to examine the degree to which data and metadata can be recovered from uninstalled medical device apps and the devices themselves. And then hopefully the insight that's gained from this avenue of research will help organizations alleviate data leakage when devices are decommissioned and or smartphone apps are removed from devices. Thank you for your attention. If you have any questions, please reach out onto the email address that's shown to you on the screen.
Good day to all. I'm sending you a lot of greetings from Zagreb. My name is Petra Zoric, and today I will present you a paper entitled Smart Factory Environment Review of Security Threats and Risks. I wrote this paper with co-authors Mario Muca and Tibor Mio Kuljanic. First of all, I will say something brief about myself. I'm currently employed as an assistant at the University of Zagreb Faculty of Transport and Traffic Sciences at the Department of Information Communication Traffic. I'm also a PhD student and I'm developing my knowledge in the Laboratory of Security and Forensic Analysis of Information Communication Systems, which is part of the mentioned department. My scientific work is focused on researching the possibility of applying information communication services in different segments of the transport system. I also had a role in organizing this year's conference as a publicity and social media chair. I must say that I'm very sorry that we are not all together here in Zagreb. I hope you and your families are doing well in this unpredictable time. Now, something about this paper. Today, I will introduce you in the topic, present you smart factory environment and the most crucial information and communication technologies in this environment. Of course, there will be words about security threats and risks that are the main topic of this paper, and for the end, conclusion. The digital transformation of the production process and the creation of added value of the services that manufacturing companies provide to end users are the Industry 4.0 environment's main features. With the Industry 4.0 concept introduction, there are changes in company strategies, business models, value chains, production processes, services, and relationships with stakeholders who participate in one production process. The topic of security in such an environment is still insufficiently researched and represented in the currently available scientific and professional literature. For this reason, this paper aims to provide insight into the most critical information communication technologies in a smart factory environment and represent the security risks and threats possible in a smart factory environment. One of the crucial components of Industry 4.0 development is a smart factory created by establishing a real-time dynamic and optimized network. As part of this network, smart sensors implemented in factories and workplaces are the drivers of Industry 4.0 and the Internet of Things. The goal of production system like smart factory is to optimize production processes fully. In one highly digitized production plant like a smart factory, all systems are interconnected and participate in the exchange of data of every aspect of production in real time. Data is a crucial aspect of smart factories. When transferring data through systems to connect all production operations, the entire facility in which the smart factory environment is implemented can learn and adapt to the business's changing needs. This concludes that smart factories are intelligent production systems that can dynamically adapt to changes that occur due to their ability to learn on the go. This achievement of a high level of automation of production processes and efficiency is enabled by using many currently available technologies. Some of the most critical: Internet of Things, artificial intelligence, and machine-to-machine communication. These technologies create specific products ordered by end users and create entire related value chains. New business models are accelerating the manufacturing industry's transformation, changing the current business methods and market structure, and establishing digital supply networks. Communication between different network parts is multidirectional, creating a link between traditionally unconnected links in the supply chain. There are 5 main features through which a smart factory can be described: connectivity, optimization, transparency, proactivity, and agility. All of these features individually can play a significant role in enabling more informed decisions and improving the production process. Given that each production process is specific and that for this reason the two smart factories are unlikely to look the same, manufacturers decide which of the features are relevant to meet their production needs. Smart factories optimize different assets and help the organization get the most out of them. It also helps an organization take advantage of all these resources synergy to gain a significant advantage in productivity and revenue. The scalable infrastructure of a smart factory environment is cost-effective because it can be easily expanded to meet the manufacturing process's growing needs. It is also important to note a smart factory sales sustainability that can replace specific roles that require repetitive and tedious activities. Equipment locked in a smart factory environment generates a large amount of data during the execution of specific actions in the production process. Such data are not structured and are usually unused. However, with the advent of Internet of Things and big data technologies, such data analysis takes place with ease. To collect data and transfer them to a platform that can analyze them, equipment must be equipped with sensors. Smart sensors have become devices with detection and self-awareness capabilities. They are designed as IoT components that convert real-time information into digital data transmitted to the gateway. Necessary technologies such as radio frequency identification to identify and track products in supply chain scenarios to smartphones and wearable equipment that have significant computing capabilities and internet connections. Such a network enables new services in the industrial sector and is known as IoT. CPS is the foundation of industrial IoT and represents computer platforms that monitor and control production's physical processes. Such systems typically communicate via closed industrial communication networks via IoT, but are often connected to the internet. This figure on this slide shows the various technologies present in the smart factory environment needed to achieve innovation and improve production processes capacity. Machine-to-machine communication in such an environment is direct and intensive and refers to a technology that facilitates direct communication between devices in a network without human assistance. In a smart factory environment, big data analytics is necessary to test vast amounts of different types of data sets generated by smart sensors or devices in real time. Artificial intelligence algorithms allow computers and digital machines to perform tasks accurately related to intelligent human beings. Machine learning algorithms, on the other hand, allow computers to operate and improve their prediction capabilities without explicit programming. Additive manufacturing technologies such as 3D printing allow creating objects of different geometric shapes by adding materials. Augmented reality in a smart factory environment is used to improve the efficiency of manual assembly tasks. Cloud computing solutions provide access to shared set of resources such as networks, servers, and applications. It is important to say how 5G network has the potential to revolutionize IoT as well as industrial IoT. In the traditional production process, the security of production was achieved with physical isolation carried out based on strict access rights management. The smart factory is connected by nature, and the essential part of the factory networks is connected to wireless networks and more expensive corporate system. Devices involved in the manufacturing process become accessible to unauthorized attacks. Each information communication system is most often defined through three fundamental principles known as the CIA triad: confidentiality, accessibility, and integrity. These principles are essential for smart factory environment functionality. Cyber attacks on a smart factory often pursue one of the following three goals: theft of personal data of end customers. Criminals use a unique integrated customer relationship management system, for example, access to the operating system through heating and air conditioning suppliers. Then interruption of the entire system. It can cause dramatic losses associated with hacker attacks. Industrial espionage and sabotage. Technology vulnerability can be exploited to steal intellectual property and gain a significant competitive advantage over competitors. Systems and machines that are potentially weak links in the security chain can be maliciously used to damage manufactured goods or cause failures are manufacturing execution system, human-machine interfaces, and industrial IoT devices. On this picture, you can see 5 attacks that were analyzed under different assumptions of the attacker model. Due to the high level of interconnection of production and information and communication components and integration based on information technology, the physical production processes operation depends on the smooth operation of information and communication services that lead to them. For this reason, smart factory networks face new threats to information communication security concerning 4 dimensions: availability, access, accuracy, and accountability. Smart factory security threats arise from 4 channels: software errors and hardware malfunctions, open internet protocols used in such an environment and standard networks, numerous parties involved in the execution of the production process, and a large number of devices that can be accessed. All components found in such a dynamic system become security critical as industrial surveillance systems become the target of malicious cyber attacks. Threats can come from various sources, such as worker activity in such an environment or hacker attacks. They can cause various damages in the business process itself and even interrupt the business. One of the most critical threats in the smart factory environment is the unusability of the on-demand service. Distributed denial of service attacks are among the most significant threats because they use multiple vulnerable systems infected with malware, and such a threat is difficult to protect for any externally accessible interface. It is important to highlight the fact how it is imperative to invest in preventive measures and active defense against attacks to ensure connected production systems. The Industry 4.0 concept represents a new way of managing production processes. With its application, connections between people, systems, and objects become more complex, creating a dynamic and real-time optimized network. The constant progress of information communication technologies applied in the manufacturing industry promises excellent potential for developing production processes, which leads to a paradigm shift in production. Emerging production systems enable automated and flexible production facilities and can economically create personalized products. Today's production systems are still not sufficiently sophisticated in terms of defense against malicious threats. This applies to attacks on CPS that can cause physical damage and endanger human life. Given the many threats to which the smart factory environment is exposed, companies are forced to implement extensive security and protection measures for information communication systems that allow a large flow of data to optimize the entire production process. To conclude, it is imperative to invest in preventive measures and active defense against attacks to ensure connected production systems. Thank you for your attention. Please feel free to contact my co-authors or me about this topic. Also, we are open for new ideas, collaboration, and suggestions for our future work. Also, I'm sending you a lot of greetings from Zagreb, and I'm hoping to see each other in person as soon as possible. Stay safe, and thank you once again.
This presentation describes the article Smart Production System with full digitalization for assembly and inspection in concept of Industry 4.0. The authors are Kamil Židek, Vratislav Hladký, Jan Piteľ, Jakub Denčák, Alexander Hošovský, and Peter Lazorik. The paper presents these subsections. The present and smart technology system consists of 3 levels of technologies: production technologies, inspection subsystem, and digitalization software system with assisted assembly process by collaborative robots combined with mixed reality device. The first technology is production technologies, which consists of small CNC, rapid prototyping device, and standardized parts storage, which is combined with collaborative robots and mixed reality device. This system provides assisted assembly work cell. The second subsystem is inspection and consists from RFID readers with passive tags, vision systems with 3D inspection and multi-spectrum light, and with device 3D profilomer for precise measuring. The last part is digitalization software, which is represented by digital twin model, which is implemented to server, and for communication uses OPC communication, which store data to cloud platform, and additional data is acquired from IoT devices. All used technologies need some digital feedback to ensure self-diagnostics with some level of adaptability and automated prediction of future status for operation as smart production system. It was defined 3 main groups of technologies which need to digitalize it. The first group is manufacturing technologies. In graph are represented by blue blocks, and second group inspection devices represented by yellow blocks, and last third group are control systems and data processing represented by green blocks, where all data must be accumulated in one place by cloud platform for knowledge extraction and complex decision plan. Visualization of extended or extracted knowledges are presented in violet blocks. The other supporting operation like storages handling and staff workplaces are in light blue blocks. All used technologies are shown in presented tables. Control infrastructure is based on Siemens devices, include RFID system and vision system, and measuring devices are from Keyence Corporation. Communication technologies for data exchange are shown in last column and is mainly based on Profinet technology, Ethernet, and OPC communication system. These slides show prototype of smart production system. On the top left is the production system designed in 3D software Autodesk Inventor before establishment to laboratory and conversion to digital model. The picture on the bottom right is institutional laboratory with smart manufacturing system and assisted assembly workplace with cooperative robot and mixed reality device. The main workplace is montage voxel with assisted assembly of the products on the fixture. The collaboration with the robots is realized by mixed reality device Microsoft HoloLens tool, which can detect worker hands and part position in assisted assembly. Collaborative robot detect parts by integrated camera and for positioning uses separate grippers and vacuums. This slide presents used vision inspection systems. Vision systems check input parts quality and output assembly surface errors. 3D profilomer check dimension of the parts before assembly process. A smart manufacturing system integrates 3 different types of RFID technology. Low frequency technology RF200, high frequency technology RF300 and ultra high frequency RF600. The picture shows the last technology, ultra high frequency. Each RFID reader has external antenna to create secondary identification gate. RFID transponders are used for fixture identification, and RFID labels are used in assembly parts. Low frequency and high frequency RFID technologies are used for part identification with smaller dimension. This slide presents the control system. The main control system is based on PLC and uses separate converter for each motor to independent speed control of all conveyors. 2 types of PLC are used: standard industrial PLC and software PLC as backup system. The main control system is on the picture in left. In the middle is the control system for vision measuring, and the right picture shows the pneumatics control box. To set up a reliable communication which is necessary for real-time data synchronization to digital model twin, it must be designed a networking structure with optimal bandwidth. Design of a networking structure for smart production system with optimal backbone is on the left picture. The control system networking is on the picture right. This slide presents a knowledge extraction system. The main system for data storage in clouds is based on rack server Fujitsu Primergy. The data backup is realized by a server HP Proliant. Data are visualized by 6 LCD panels for monitoring production process and error localization. All used technologies were included to simulation software to evaluate timing and optimization of production process. It was used Technomatics software. This model can be connected to real control system by OPC communication to visualize real-time production process. The model can be switched between 2D or 3D representation to show error localization or production process delay for operation inspection. This slide presents the example of data digitalization. The inspection system consists of two industrial vision systems. The first with multispectral light, RGB light, infrared light, and ultraviolet. And second, have a 3D feature acquisition by structural light for product error detection in 2D or 3D for final assembly check as output product inspection. The last technology is 3D profiler and check the dimension of manufactured parts in real time in fixture during movements. The picture on the left shows the multispectrum image. The picture in the middle represents 3D model color map acquired by structural light, and on the right is 2D graph of measuring from 3D profiler. There is some examples of cloud data visualization. The experimental smart production system uses two different cloud platforms for data collection: commercial MindSphere with OPC data and open source Grafana with Influx database for IoT data collection. The Tinger I/O was used for graphical output from simulated EOT device and education purpose. The picture on the left is from MindSphere cloud platform. The middle picture represents some example data from Grafana visualization system, and for simulation on the right is the picture from Tinger I/O, especially used for IoT devices, but there is used from simulated data. The conclusion and next works. This paper presented smart production system with full digitalization based on cutting-edge technologies from inspection system and data knowledge extraction by cloud platform. The smart production system can be handled by two people, one for maintenance, monitoring and engineering, and second for manual work like input-output storage, service, and assisted assembly task. The future works will be implementation of web interface for product customization by users and automated activation of manufacturing. Thanks for your attention.
Dear colleague, at the beginning let me introduce myself. My name is Stella Hrelova and I come from Technical University of Košice, Faculty of Manufacturing Technology, Slovakia. I would like to present the paper of authors Stella Hrelova, Jozef Husár and Lucia Knapčíková, Production Quality Control using the Industry 4.0 concept. The presentation is divided into 4 parts. First, introduction. Second, tools and methods. Then, design of information flow and conclusion. Introduction. Today's manufacturing companies pay attention to the conformity of product with technical standards, but at the same time they understand the quality more comprehensively. They see that quality that satisfies the customer as a basic strategy to ensure their competitiveness. It means that improving quality will significantly increase the profitability of the product and will act as a key strategic factor in the market. The traditional approach of improving product quality has its limitation and does not allow active intervention in the production process. A possible solution is to use the Internet of Things approach, which allows manufacturers to analyze product data that is generated from devices, and thus they are informed about the quality of the production process in the real time. The role of IoT is to connect a large number of heterogeneous terminals and provide the data obtained for all kinds of different digital services. Implementation of Internet connection enables the provision of computing power and the application of scanning, counting, communication, and environmental control. In this paper, I'll describe some technologies which can fulfill the Industry 4.0 concept in terms of the network concept of digital objects interconnection, collection, exchange, analysis, and distribution of data among objects in industrial enterprises. Tools, IoT. According to one of many definitions, it is a network of interconnected objects that are uniquely addressable. The network being based on standardized communication protocols for exchanging or sharing data and information in order to achieve higher added value. IoT is thus a concept for physical and virtual objects, TICs, that can share data through the Internet. It is also possible to see that the Internet of Things is one of the main sources of big data. The application of this technology to production creates a new concept, the Industrial Internet of Things, IIoT. The figure represents parts of Industrial Internet of Things. They are connections, things, data, control, communicate, process. Vision system. These systems are used in all industry areas and are an essential part of achieving efficiency in high-quality standards. Industrial machine vision systems are typically implemented in automated lines with manipulators or industrial robots to inspect, identify, diagnose, measure, count, and track products. In most cases, industrial automation systems are designed to inspect known objects in fixed positions, characterize faults on items, and take steps to report and correct these faults and replace or remove faulty parts from the production line. These systems are also described as computer systems where the software performs tasks for acquiring, processing, analyzing, and understanding digital images. They are usually focused on industrial quality assurance, defect detection, part recognition, etc. They form eyes that capture the process and recover the analyzed digital image using images special processing software. The basic principle of the machine vision system is that the camera captures images that are sent to the computer via one type of the serial communication protocol standard. Obtained images are subsequently evaluated in computer according to a set of rules. For assumed system, it is a very important part because of its ability to detect the wrong parts of objects. This aim can be fulfilled using various methods. Nowadays, there are used various methods of artificial intelligence to recognize that object. This system has advantage over the other techniques in that the integration of vision-based inspection system reduces production time, increases the efficiency and quality of inspection activity by eliminating human interaction in the inspection process. The figure represents the real camera, which is a part of our proposed information flow. Radio frequency identification, RFID. It is a technology that has gained popularity in many business sectors thanks to the relatively wide area of its application in many industries. RFID is a technology that is used to identify objects and transmit information from a distance via radio waves. Different types of RFID tags are used for different applications. The advantage of RFID system is that many objects can be detected automatically and almost simultaneously without visual contact. RFID system consisting of one or more readers and several tags also play a key role in the IoT attitude. These technologies help automatically identify everything to which they are connected and allow objects to assign unique digital identities, integrate them into a network, and associate them with digital information and services. In the proposed information flow, we assume using the programmer logic controller PLC, which are described as a reliable control system that can continuously monitor the status of devices connected to their inputs. Cloud computing. Cloud computing offers a model for on-demand access to share computing resources, configurable networks, servers, storage, applications, and services which can be rapidly provisioned. The idea is to provide a flawless data processing capacity. Cloud computing has changed the way technologies can be assessed, managed, and delivered. Cloud storage is a computer data storage model in which digital data is stored in logical files that are said to be located in a cloud. Physical storage is spread across multiple servers, sometimes multiple locations, and the physical environment is usually owned and managed by the host company. Cloud and IoT is a platform that enables intelligent use of application, information, and infrastructure in a cost-effective way. Although IoT and cloud computing are different, their properties are almost complementary. In the presented proposal of information flow, we assume the storage of obtained data in the database, which should serve as tool for various outputs based on individual queries, as well as a source of basic information about the product. For the proposed information flow, we assume the storage of individual parameters using database software. An already created database scheme with clear items is assumed, into which information will be written through individual supporting technologies. The following scheme shows the expected information flow of the workspace. Position 1. The initial product information, for example, information from the drawing documentation, ID numbers, etc., is read using RFID technology and sent to the PLC. RFID tags can be attached to the pallet, and RFID readers and antennas are placed at fixed workstation to monitor the entry or exit of these pallets. Through wireless identification, these tags can communicate with RFID readers to obtain real-time data and possibly decide on further material flow. The information continues through the server to the database on the cloud storage. The product continues with further production operation, and in a certain state of development it is necessary to check the current quality. Position 2. For example, to assess the key dimension of the product, whether it meets the requirements, or to find out the correct location during assembly, etc. At this point, a camera system can be used which evaluates the set parameters and sends the information via PLC again to the database, where the added information will be paired based on the agreed rules. The course of individual product is displayed at the control station 3. As a part of the quality assessment at this point, lean tools and methods can be used where a warning system, for example, and then can be applied, which in case of non-compliance will signal an error. If the required parameters are met, the product proceeds with the further operation until it reaches the last required item 4. Data is reloaded to the database from the item via RFID. The data storage in the database can then be displayed on various devices, computer, tablet, or mobile phone. Accessibility of individual data will be ensured at several levels of management. In the near future, the goal is to expand the experimental workplace with other objects, for example robots, and create an experimental automated line where the possible use and interconnection of the described technologies and tools would be tested. The next figure shows experimental workspace. Conclusion. Today, data is one of the most important areas of interest in any business. By using the latest trends and technologies, companies try to obtain and analyze as many relevant data as possible, which would allow them to assert themselves, respectively remaining in the market. In this paper, the anticipated information flow is proposed with the application of various current high-performance technologies and tools. All the described technologies have great potential to bring the required data in shape with the right configuration regardless of place and time. Companies thus gain important information for the presentation to the potential new customers and can strengthen their position with existing customers.
Dear participants of the conference, I'd like to present the research of our faculty, Multifunctional Smart Air Cleaner. Air contamination is a very acute problem in our modern society. Environmental air quality often affects human health. Allergens, viruses, bacteria often float in the air and settle on the surfaces. We spend about 90% of our time indoor, at home, at school, and so on. Poor indoor air quality has been linked with not only with the long-term disease, but with the momentary spread of respiratory tract infections. There are many technical solutions for home, such as air humidifier, recuperator, purifier, and so on. All these devices fulfill their functions at home, but what solution is appropriate for offices? Usually, home devices have pre-filter, dust filter, ionizer, UV lamp. Construction of device provide indoor air movement. During this process, dust particles will be captured by filter and smaller particles will be disinfected by UV light. Large people flow in offices require more devices or more powerful devices to provide comfortable work conditions. The pandemic situation has introduced additional rules to be followed. More often disinfection of surfaces, minimum of 3 times per work shift, more often aeration of room, and should be provide the 15 square meters for each client. To select more optional device for disinfection, it is necessary to refer to specific parameters of existing cleaning elements. All cleaning elements has its own disadvantages. For example, HVAC system has one function, it is climate control. PRAC requires constant cleaning of elements, namely filters. UVA and UVB lamps not able to deactivate enough bacteria. UVC light is not friendly for skin. HEPA efficient only for biggest particles. Also, there is practical problem with all home devices, namely, they are not equipped by sensor which signalize about dusting of filters. Indoor air pollutants have diverse nature. That is why they can be not only in the air but in the building materials, outdoor air, and transported by people. Recent inventions more often basis on the using UVC light for disinfection of surfaces and environment. The properties of the UVC light were known from the 1892, and the latest research of World Health Organization has been shown that the UVC light deactivates about 100% of bacteria. The greatest examples of the pandemic inventions are shown on the picture. For example, warehouse robot disinfector, UVC mask cleaner, and portable UVC sterilizer. Using all the best features of the home purifiers and popular smart technologies was designed multifunctional smart air cleaner. The main components of the device are 3 16-volt UVC lamps with the life cycle about 8,000 working hours, 2 fans that handle 50 square meters per hour and at the normal mode, 2 LED strips for lighting the room. Device is also equipped by manual and remote control. To ensure comfortable working conditions for employer were proposed 3 modes: LED lamps and air purifier, the second one disinfection of the surfaces, and third one disinfection of the surfaces and air, where the first mode using for normal working conditions with workers and customers indoor. The device provides light in the room and fans move air through the device and disinfect it. The second mode activates when there are no people in the room and there is required to disinfect the surfaces. The third mode activates fans and UVC lamps to clean air and surfaces. This mode is appropriate to active work shift when the number of customers was maximum. The optimal control of the UV and the LED light is ensured by EOT Smart Control Unit with external sensor. Sensor directs the movement of people indoor and signalizes about needed intensity of the fans or lamps. The multifunctional smart cleaner will help to disinfect not only the air of the room but also the surfaces, as well to eliminate the room. The 3 modes of operation will help to efficiently manage the device and control intensity of the fans and lights. The basic mode controls the optimal mixing of the light, white and blue light in the presence of the people. The sensor will signalize about the number of the people in the room. The smart control of the device will provide connection with the mobile device and also the cleaning element with the internet and signalize about all problems with the device. The smart cleaner will be integrated to the smart home systems and can be switched on remotely. The control of purifier filter contamination is very important also. That is why the people will have information on the hand with the help of mobile application. Since the idea of smart integrated control systems is constantly evolving, it is assumed that the proposed device will provide comfortable working conditions not only during the pandemic, but also in peacetime and will meet all the requirements of our time. Thank you for your attention.
Dear colleagues, my name is Dmitry Nikov, and I am pleased to present our project about the application of Gaussian processes for magnetic field maps estimation, which is done together with Stefan Henzel, Marin Marinov, and Timish Fiuk. Let me outline the structure of this presentation. First, I will begin with a short introduction and the motivation behind that work. Afterwards, I will briefly describe the methods and the experimental setup, and I will conclude with a discussion of the results. Object localization has always been a great deal of interest, and while outdoor localization has been already somewhat worked out with a combination of satellite navigation and inertial sensors, the problem arises when the objects are placed inside the buildings. Indoor localization is still subject of active research. Since the early days of navigation, people rely on geomagnetic fields to find their ways around. Moreover, the improvements in cost-effective sensors, it is possible to create the maps of geomagnetic field in the buildings. These maps will show a heavily distorted geomagnetic field because of the presence of constructions, materials, and furnishing. Those disturbances, however, are local and mainly stationary, and that could be used as a feature to determine object position. The aim of this work is to create a map, geomagnetic field map inside the buildings with the usage of mobile robots. What methods did we apply throughout this work? First, a robot moves around and measure its position and magnetic field. The position of the robot is determined by the fusion of inertial sensors, mainly acceleration and rotational rate sensors, with the odrometry data and the distance from the depth sensing camera. Those data samples are later fed into the particle filter that enables simultaneously localization and mapping, so-called SLAM algorithm. And SLAM algorithm provides output data, the position and the two-dimensional raster map of the environment. Later, the magnetic field is calculated using the position and the measurement of the commercially available magnetic field sensors that are attached to the robot. As a robot's position is not completely known, the map generation process must take into account the uncertainty in the robot position. The uncertainty is due to environmental influences and noisy sensors. The figure shows the mapping with the data where only a robot has moved and measured the magnetic field. In order to create the two-dimensional map or three-dimensional map, we need to predict the values of the geomagnetic field for those missing points. And to predict these values for the map generation, and the processing of the associated uncertainty in the form of covariance, the appropriateness of Gaussian processes was investigated. As a Gaussian process is a collection of random variables, any finite number of which have a joint Gaussian distribution, they can be applied for an estimation of continuous and smooth functions that describe measured data. We use a Gaussian process to describe distribution over function. Gaussian processes can be applied to a variety of machine learning problems, mainly interpolation with splines, classification problems, or data prediction. A special case of a Gaussian process regression that is used throughout this work is known in geostatistics as scridging. As you can see in those examples, what is the influence of case of one measurement point, two measurements, or three measurements of the different confidence intervals and the functions that is resulted. And the selection of the specific covariance function depends on the domain of available knowledge about the underlying process. In our case, we considered the behavior of the magnetic field in the closed spaces. The problem of inference requires estimating the parameters of these covariance functions using measurements. The parameters are referred to as so-called hyperparameters. One of the most popular covariance functions is a stationary exponential distribution, so-called radial basis function. And hyperparameters of the radial basis function are sigma squared and LRBF, which express the scale and granularity of the function. On your right-hand side, you can see the influence of the hyperparameter LRBF on the estimated functions and the covariance intervals. The estimation of we estimate the hyperparameters by determining the maximum a posterior probability. The use of Gaussian process not only allows for the integration of all uncertainties occurring in the mapping, but also allows for subsequent merging of the created maps based on estimated accuracy. And this is possible by recalculating the map with all measurements or by measuring several interpolated maps with a weighted arithmetic mean based on covariance recorded at arbitrary times with any sensors. Let me describe our experimental setup. The structure of our recording measurements consists of central PC, robot, and sensors that are magnetic field sensor and inertial measurement unit that are able to measure the magnetic field and the inertial parameters. The robot is a turtlebot, a mobile robot system which is able to move around. The middleware was the robot operating system, which allows for easy driver connection. And the inertial measurement unit actually consists of 3-axis rotational rate sensor and 3-axis acceleration sensor that is integrated into the single chip and connected to the host PC that is placed on the robot. Magnetic field sensor is a 3-axis MEMS magnetic field sensor HMC 5883L that is used to record the magnetic field. The positioning of the sensor the positioning of the robot is done through a simultaneously localization and mapping algorithm. By calculated position of the system, the inertial measurement unit allows to obtain the projection to the 3-dimensional magnetic field measurements into the global coordinate system, and thus to determine the flux density components by the different X, Y, and Z directions. The resolution of the magnetic field is a 0.5 microtesla with a measurement range of plus minus 800 microtesla, and the deviation is 0.2 microtesla. The magnetic flux density was measured in the X, Y, and Z directions, but we need to clean those measurements. And how we clean them? By removing the single outliers with using median filter of 5th order. And because of the slow moving robot, the magnetic field cannot change quickly, and these measurements were subsequently smoothed by the moving average filter after rejection the outliers with the median filter of 5th order. Later, the size of the kernel varies between the different measurements and must be periodically adjusted. For a large part of the experimental results, in case of investigated magnetic field is very irregular, a kernel size of 100 was chosen. In areas where there is a homogeneous magnetic field and there are only separate regions in which magnetic field strongly fluctuates, the filter kernel was reduced in size so not to completely remove the measurements. The inertial measurement unit and the odometry of the turtle boat use different sampling frequencies, and the measurements have to be put into correspondence. They need to be synchronized. And thus, the magnetic field density and the time should be assigned to a point in Higgs-Y plane, and with the correspondence with the time. Now, we need, because of the construction of our measurement runs of the turtle boat, there is a slight misalignment between the internal inertial measurement unit and the magnetic field sensor. This should be corrected, and we corrected it through the following corrected pair of values. We calculate the distance and the angle, and then when we subsequently process the data, we take into account this misalignment. Here you can see the exemplary result of the trajectory of our robots, and the associated uncertainty is visualized with ellipse based on actual covariance. To create a magnetic field map from a driven path, different interpolation methods exist. The method used here is based on Delaunay triangulation. This means that triangles are formed between pairs of points in space. Those triangles are chosen to avoid long thin triangles, since the triangles cover the entire grid and do not overlap. A value can be assigned to each point of the grid. Let me describe the results. Since the magnetic flux density B is a vector field, but only one scalar can be interpolated between X and Y, some consideration has to be made. It is conceivable to interpolate every one of the measurement components of B, of the magnetic flux density field. In further course, the measured value of B in Higgs direction are described as a MB of Higgs. Similarly is the same of magnetic field in Y direction and Z direction. A two-dimensional interpolation is performed in order to get the magnetic field value. From these three interpolated maps, it is now possible to generate a map of absolute value of magnetic field. For this, however, it is necessary to refer the values to a global coordinate system. Since the turtle boat can only rotate around z-axis, the necessary transformation results as follows. Where R is a rotational matrix as a function of orientation angle and can be shown here. The absolute value of the magnetic field in different directions could be given as follows. Now, the experimental runs in several environments have proven small to little influence of the magnetic field vector in z direction over the sensitivity to overall field strength. This is due to considered scenarios where the robot is mainly operating in the industrial or home environments, where the ceiling is too far away and have any influence, and commonplace objects rather extend to the floor and thus permit to drive under. Therefore, vertical magnetic component can be omitted, which significantly speeds up the interpolation and combination of the measurement data. The overall field strength of the magnetic field in X direction and Y direction could be given as follows. In the initial study, the suitability of Gaussian processes for interpolating measured data was examined. For a comparison, we applied the classical two-dimensional linear interpolation, as you can see on your right-hand side here. This is the result of classical linear interpolation. And it is clear that Gaussian process interpolation have a qualitative advantage over the linear interpolation, and thus why it is used here. Magnetic maps were recorded based on several test runs in different areas of the university. The figure illustrates the qualitative results for a small area of the laboratory. The Gaussian regression is fundamentally suitable for producing a complete and usable map for individual measurements. The maps created have a good degree of detail. The advantages compared to less expensive methods lie in the simple integration of new measurements, the availability of the quality measure in the form of covariance matrix, and based thereon natural integration into stochastic localization methods. The modeling also allows for introduction of boundary conditions and model knowledge. However, all this is at expense of the extensive calculations. Maps were created with a resolution of 5 centimeters. The potential for positioning accuracy is within few decimeters to meters, which is already sufficient for a continuous improvement and drift correction of the inertial sensors. And with this, I would like to thank you for your attention. And if you have any questions, please do not hesitate to contact me. Thank you for your attention.
Dear participant, dear ladies and gentlemen, after 2 days of great conference, we are starting with the last part of the conference, the closing ceremony. So in this part of conference, we must to decide which paper is the best paper, and after not too easy task, program committee decided to choose one paper as a best paper for the best paper award. So we decided to introduce the best paper for you, the self-organized adaptation of spreading factors for LoRa radio late based on experimental study from authors from Germany. So from our decision, it's the best paper for this conference. Thanks very much to authors for provide us with this great paper for this conference. And for the end, just few information about just to remember the organizers of this conference. And the last information for the end of the conference is that I would like to see you all in the next one, Fabulous conference. I hope that we will be stronger than COVID. And I hope see you all in the Fabulous in Zagreb, Croatia, in live mode. Thank you very much and be healthy. Thanks. Ciao.